What if you could step through a doorway and instantly be on the other side of the galaxy? Picture a tunnel carved through the very fabric of the cosmos, a shortcut not just across space, but across time itself. This isn't just a scene from a science fiction epic. It's a genuine possibility rooted in the edges of our understanding of physics, a concept that has captivated the brightest minds for over a century. The idea of the wormhole taps into our most fundamental human desires: the thirst for exploration, the longing to reach the unreachable, and the audacious dream of conquering the vast, silent distances that separate the stars. It's a vision that feels both ancient and utterly futuristic, a promise of a universe that is far stranger and more interconnected than we ever dared to believe. This incredible journey begins with the work of Albert Einstein, whose theory of general relativity gave us our modern picture of gravity, not as a force but as the bending and warping of space and time. His equations hinted at the existence of bridges in the cosmos, theoretical passages through this warped landscape that could connect two distant points. Since then, these wormholes have become a playground for theoretical physicists and a boundless source of inspiration for storytellers, living in that thrilling space where hard science meets limitless imagination. They represent one of the most exciting and mysterious frontiers in all of physics, a puzzle that challenges everything we think we know about the rules of the universe. Today, we're embarking on a grand tour of this enigmatic concept. We will navigate through 30 of the most incredible, mind-expanding theories about wormholes and space-time travel. We'll explore how they might form, how they could potentially be stabilized, and the wild hypotheticals about what traveling through one would actually be like. From traversable tunnels and cosmic shortcuts to their potential roles as time machines and their deep connections to the very birth of the universe, this journey will stretch your perception of reality. So get ready to dive deep into the science and the speculation, because we are about to unlock some of the cosmos's most closely guarded secrets and venture into the great unknown. Our journey into the unknown starts not with science fiction, but with a set of equations on a blackboard. The very first concept of a wormhole emerged from the pure, unadulterated math of Albert Einstein's theory of general relativity. In the 1930s, Einstein, working with physicist Nathan Rosen, discovered something peculiar embedded within the solutions to their field equations. They weren't looking for cosmic tunnels, they were diligently working to model elementary particles using only the geometry of space and time. What they stumbled upon was far grander. Their calculations revealed the possibility of a structure that looked like a tube or a bridge connecting two distinct regions of spacetime. This was the birth of what we now call the Einstein-Rosen bridge. Think of spacetime not as a static stage, but as a flexible, dynamic fabric. A massive object like a star creates a deep depression in this fabric. That's what we experience as gravity. Now, imagine that this fabric could be pinched and folded in such a way that two distant depressions are connected by a narrow, ultra-short passageway through a higher dimension, a kind of cosmic subway tunnel that bypasses the long, winding road on the surface. That's the essence of the Einstein-Rosen bridge. It was a direct mathematical prediction that the universe might permit these incredible shortcuts. However, there was a monumental catch that prevented early physicists from getting too excited about interstellar travel. The original Einstein-Rosen bridge was intrinsically linked to another prediction of general relativity, the black hole. In their model, the entrance to this tunnel was what we would identify as a Schwarzschild black hole, a point of infinite density known as a singularity. The bridge itself was incredibly unstable. Theoretical models showed it would pinch off and collapse into that same singularity in an infinitesimally small amount of time, long before any object, let alone a spaceship, could ever hope to traverse it. It was a one-way street to a cosmic dead end, not a highway between stars. This is precisely why, for decades, these bridges were seen as little more than mathematical curiosities. They were fascinating artifacts of the equations, beautiful in their symmetry and implication, but they were deemed utterly impractical. They existed in the realm of theoretical physics as a proof of concept, a demonstration that the fabric of the cosmos could, in principle, be woven into such a tunnel. But if you tried to use it, it would snap shut behind you. So, while the seed of the idea was planted by Einstein and Rosen, it would take many more years and much more radical thinking for the wormhole to evolve from a cosmic dead end into a potential doorway to the stars. The next great leap in our understanding came from a physicist who saw past that initial dead end and asked a revolutionary question: what if we didn't just accept the collapse? What if we could find a way to prop the door open? This brings us to the pivotal idea of the traversable wormhole, a concept that transformed the wormhole from a mathematical ghost into a potential engineering project. The key figure here is John Archibald Wheeler, the scientist who actually coined the memorable term wormhole in the 1950s. But it was his student Kip Thorne who, decades later, took the idea and ran with it, inspired by a rather unusual query. The call came from none other than the astronomer and science communicator Carl Sagan, who was working on his novel Contact and wanted a scientifically plausible method for interstellar travel. Thorne and his colleagues took on the challenge, and in doing so, they turned science fiction into a serious theoretical physics problem. Their work revealed a fundamental distinction. The old Einstein-Rosen bridge was a non-traversable wormhole. It was a feature of the space-time geometry around a specific type of black hole, a structure that was born and died in a flash, impossible to enter or exit. A traversable wormhole, in stark contrast, is a stable, navigable tunnel. Think of it as the difference between a rickety rope bridge that snaps the moment you set foot on it and a sturdy, reinforced tunnel through a mountain, complete with lights and a smooth road. For a wormhole to be traversable, it must meet several strict conditions. Its throat, the tunnel section, must be free of any deadly singularities, those points of infinite density that crush everything in a black hole. Furthermore, the gravitational forces and tidal forces inside the tunnel must be mild enough that a spacecraft and its crew wouldn't be stretched into a stream of atoms, a process physicists colorfully call spaghettification. So how do you build such a thing? How do you keep the throat of this cosmic tunnel from pinching shut under the immense pull of its own gravity? This is the central puzzle, and the theoretical solution is as bizarre as the wormhole itself. To counteract the natural tendency of the wormhole to collapse, you need to line the throat of the tunnel with something very special, something that possesses what physicists call negative energy density, or more broadly, exotic matter. Now, this doesn't mean antimatter. Antimatter has positive energy density, and when it meets normal matter, results in a tremendous release of energy, the opposite of what we need. Exotic matter is a hypothetical substance that defies our everyday experience. According to general relativity, gravity is always attractive because all known forms of matter and energy create a positive curvature in spacetime, like a weight on a rubber sheet. Exotic matter would do the opposite. It would create a negative curvature, effectively propping spacetime open, acting like a kind of anti-gravity force that pushes the walls of the wormhole apart, preventing the catastrophic collapse. You can picture this with a simple analogy. Imagine the wormhole's throat is like a tiny, flexible straw. The natural gravitational pull is like you trying to suck a thick milkshake through it. The straw walls collapse in on themselves. Now, imagine you could somehow make the straw rigid, reinforcing it with a material that actively pushes outward, resisting the inward pressure. That reinforcing material is the exotic matter. The search for this material takes us to the very edges of known physics. Intriguingly, the quantum world offers a glimmer of possibility. The Casimir effect, a well-demonstrated phenomenon in quantum field theory, shows that two perfectly smooth, uncharged metal plates placed extremely close together in a vacuum will experience a slight attractive force. In the space between those plates, certain quantum fluctuations are excluded, resulting in a region that effectively has a lower energy density than the surrounding space, a form of negative energy density. While the amount generated in such an experiment is minuscule, it provides a crucial proof of principle that the laws of quantum mechanics do, in certain circumstances, permit the existence of negative energy. The challenge, of course, is scaling this quantum quirk up to the astronomical levels needed to stabilize a wormhole throat, a task that remains firmly in the realm of theory for now. But what exactly is this exotic matter, and how could something with negative energy possibly exist? To understand this, we need to shift our thinking from the familiar world of classical physics to the bizarre, probabilistic realm of quantum mechanics. In our everyday experience, energy is a positive quantity. A moving car, a lit light bulb, a warm cup of coffee all possess positive energy. This positive energy creates the attractive force of gravity we all know. Exotic matter, however, would flip this script. It would possess a negative energy density, meaning that in a given volume of space, the energy is actually less than the energy of empty space, of a pure vacuum. This isn't just a lack of energy, it's a deficit, and according to Einstein's equations, such a substance would generate a gravitational repulsion, a kind of anti-gravity that pushes things apart instead of pulling them together. This repulsive force is the theoretical key to propping open the throat of a wormhole, preventing the immense gravitational pull from collapsing the tunnel into a singularity the instant it forms. One of the most promising places to look for hints of this strange substance is in a well-demonstrated quantum phenomenon known as the Casimir effect. Imagine two perfectly smooth, uncharged metal plates placed incredibly close together in a complete vacuum, a space utterly empty of all matter. In classical physics, nothing should happen. But in the quantum world, the vacuum is not empty. It is a seething, bubbling foam of virtual particles. These are particle-antiparticle pairs that spontaneously pop into and out of existence, borrowing energy from the vacuum for a fleeting moment before annihilating each other. Now place those two plates very close together, closer than the wavelength of most of these virtual particles. This restricts the kinds of quantum fluctuations that can occur in the narrow gap between the plates. Specifically, only virtual particles with very short wavelengths can appear between them, while outside the plates, virtual particles of all wavelengths can fluctuate freely. This difference in activity creates a subtle pressure imbalance. There are more virtual particles pushing on the outside surfaces of the plates than on the inside, resulting in a net force that pushes the two plates together. From an energy perspective, the region between the plates has a lower energy density than the surrounding vacuum. It effectively has a negative energy density relative to its environment. This is a genuine, laboratory-verified instance of the kind of negative energy that wormhole theory requires. The challenge, of course, is one of scale. The Casimir effect produces only a minuscule amount of negative energy, enough to move tiny plates fractions of a millimeter. Stabilizing a wormhole throat large enough for a spacecraft, however, would require astronomical quantities of this exotic material, concentrated and sustained in a specific configuration. The energy requirements are almost beyond comprehension. Some calculations suggest you would need the negative energy equivalent of the mass of Jupiter or more, just to keep a 1-meter-wide wormhole open for a single second. Furthermore, there are profound theoretical hurdles like the averaged null energy condition, which suggests that while negative energy can exist in small amounts for short periods, it might be fundamentally impossible to collect and maintain it in the large, stable quantities needed for a traversable wormhole. This doesn't necessarily mean it's impossible, but it does mean that if exotic matter is the solution, it would require a mastery of physics and engineering far beyond our current capabilities. leaning into technologies that can manipulate the quantum fabric of spacetime on a grand scale. Beyond the Casimir effect, other theoretical avenues for generating exotic matter exist, each more speculative than the last. Some models in quantum field theory suggest that specific configurations of fields could, in principle, create regions of sustained negative energy. Another fascinating connection lies with dark energy, the mysterious force causing the accelerated expansion of the universe. Dark energy also has a repulsive gravitational effect, and its energy density can be mathematically described as having a strong negative pressure. While dark energy is diffuse and uniform across the cosmos, unlike the concentrated exotic matter needed for a wormhole, it demonstrates that a form of energy with repulsive gravity is not just a theoretical fantasy. It appears to be a dominant feature of our universe's evolution. This parallel gives physicists a compelling reason to continue exploring the properties of negative energy, as understanding one of these cosmic mysteries could very well illuminate the path to solving the other. While the idea of using a wormhole as a cosmic shortcut across space is revolutionary, its potential as a time machine is arguably even more profound, stretching the very definition of what we consider possible. This brings us to a concept that sounds like it's lifted straight from the pages of science fiction, yet it emerges directly from the well-established principles of Einstein's theory of relativity. Theoretically, a stable, traversable wormhole doesn't just connect 2 points in space, it connects 2 points in spacetime, and because time and space are interwoven into a single continuum, manipulating one inevitably affects the other. The key to unlocking time travel lies in a phenomenon called time dilation, a proven effect where time itself passes at different rates depending on your speed or your proximity to a powerful gravitational field. Let's construct a theoretical scenario to see how this could work. Imagine we have a stable wormhole with 2 mouths, which we'll call mouth A and mouth B. At the start of our experiment, both mouths are right next to each other here on Earth, and their clocks are perfectly synchronized. Now we decide to take mouth B on a journey. We load it onto an incredibly fast-moving spacecraft, one that can travel at a significant fraction of the speed of light. According to Einstein's special theory of relativity, as the spacecraft accelerates and cruises at these phenomenal speeds, time for mouth B will begin to slow down relative to the time experienced by the stationary mouth back on Earth. This isn't a mechanical error, it's a fundamental feature of the universe. Time literally stretches for the fast-moving mouth. Alternatively, we could achieve a similar effect by placing mouth B in an extremely intense gravitational field, like the vicinity of a neutron star. According to general relativity, gravity also warps time, causing clocks to tick more slowly the deeper they are in a gravitational well. After a journey of, say, 10 years from the perspective of Earth and mouth A, our spacecraft returns and we park mouth B back right next to mouth A. Let's look at the clocks. For everyone on Earth, 10 years have passed, but for mouth B, due to the effects of its high-speed travel, perhaps only 1 year has passed. This is the crucial, mind-bending result. The 2 mouths of the wormhole are now out of sync. They remain connected by the spacetime tunnel, but they exist at different moments in time. If you were to peer through mouth A, you would see not the present-day location of mouth B, but its location as it was 9 years in the past relative to Earth's timeline. Conversely, looking through mouth B, you would see 9 years into Earth's future. The wormhole has become a bridge not just through space, but through time itself. Now for the truly extraordinary part, walking through this tunnel. If you step into mouth A on Earth in the present day and walk through the wormhole, you would exit from mouth B into the outside universe 9 years in the past. You have traveled backward in time. This creates what physicists call a closed time-like curve, a path through spacetime that loops back on itself, allowing an object to return to its own past. The implications are as staggering as they are paradoxical. What happens if you meet your younger self, Could you alter a past event in a way that prevents your own journey? This immediately brings to mind famous conundrums like the grandfather paradox, where you might theoretically prevent your own grandfather from meeting your grandmother, thereby making your own birth impossible. The existence of such paradoxes is a major reason many physicists are deeply skeptical that nature would allow for this kind of time travel to the past, suggesting that some as yet unknown law of physics, perhaps from the realm of quantum mechanics, might act as a chronology protection conjecture to prevent these causal loops from ever forming. Yet the fact that our best current understanding of gravity and space-time general relativity does not explicitly forbid such a configuration is a thrilling and deeply mysterious frontier. It suggests that the universe's rulebook might be more flexible or more bizarre than we ever imagined. This theoretical possibility forces us to confront fundamental questions about causality, free will, and the very nature of reality. While the engineering challenges of creating and stabilizing such a wormhole are unimaginably vast, the mere mathematical possibility that wormholes could function as time machines reveals just how deeply interconnected space and time truly are, and how much we have yet to learn about the cosmic arena in which we live. This tension between the theoretical possibility of time travel and its deeply paradoxical consequences led one of the greatest scientific minds of our time to propose a cosmic safety mechanism. Stephen Hawking, while fascinated by the implications of general relativity, was famously skeptical about time travel to the past. He once quipped, "Where are all the tourists from the future?" This intuitive argument that we see no evidence of time travelers in our present formed the backdrop for his more formal scientific proposal, the chronology protection conjecture. In essence, Hawking suggested that the laws of physics, particularly when general relativity is merged with quantum mechanics, contain built-in safeguards. These safeguards would prevent the formation of closed time-like curves, effectively making the universe safe for historians by outlawing time travel to the past and preserving a consistent, linear flow of cause and effect. But how would this protection work? It's not that a cosmic police force appears to shut down your time machine. Instead, Hawking and other physicists theorized that the mechanism is baked into the very fabric of reality through the bizarre laws of quantum physics. Imagine setting up our wormhole time machine with its two mouths out of sync. Now, consider what happens to the vacuum of empty space in this scenario. In quantum field theory, empty space is not truly empty. It is filled with a sea of virtual particles flickering in and out of existence. Normally, this quantum foam is a random, harmless background sizzle. But when you create a closed time-like curve, you introduce a profound twist. A single virtual particle could, in theory, travel through the wormhole and emerge in its own past, then travel through again and again and again. This creates a catastrophic feedback loop. The same particle exists in multiple copies of itself along the timeline, and with each loop it adds its energy to the system. This isn't like a sound system feeding back with a screech. This is a fundamental energy disaster. The energy density of these looping particles would build up exponentially, rocketing toward infinity in an infinitesimally short time. This infinite energy surge would warp spacetime so violently that it would likely tear the wormhole apart from the inside out, collapsing the tunnel long before any macroscopic object, like a human or a spaceship, could ever hope to step through. The wormhole time machine would be destroyed by the very quantum processes it sought to harness, thus protecting the chronology of the universe from paradox. The conjecture isn't a proven law, but it represents a powerful insight that the marriage of quantum mechanics and gravity might naturally resolve the paradoxes that pure relativity alone seems to permit. Of course, the scientific conversation doesn't end with Hawking's conjecture. This is an active area of debate, and some physicists propose alternative resolutions that don't involve the destruction of the wormhole. One compelling idea is that the universe might allow time travel, but it would simply forbid the paradoxes from occurring in the first place. This is often framed through the concept of self-consistency, championed by physicists like Igor Novikov. The Novikov self-consistency principle posits that if time travel to the past is possible, then any actions taken by the time traveler were always a part of history. You couldn't change the past because your attempt to do so was already part of the events that unfolded. You might think you're going back to prevent a disaster, but your actions would inevitably, through a complex and unchangeable chain of events, lead to that very disaster occurring. In this view, the timeline is a single, immutable knot. You can travel back to witness or even participate in events, but you cannot alter the established outcome. The universe conspires to ensure that history remains consistent with itself, making paradoxes physically impossible rather than dynamically destroying the time machine. While we often picture wormholes as vast, star-spanning tunnels capable of carrying spacecraft, some of the most profound theories suggest their true nature is almost impossibly small, woven into the very foundation of reality itself. To find them, we have to zoom in past atoms, past subatomic particles, down to the very smallest possible units of space and time. This is the domain of the Planck scale, a realm so tiny that our conventional concepts of a smooth, continuous spacetime completely break down. Here, at this fundamental level, the vacuum of space is not calm and empty. Instead, it is a seething, turbulent ocean, a chaotic froth of spontaneous activity that physicists call quantum foam. The idea of quantum foam emerged from the work of John Wheeler, the same visionary who gave us the term wormhole. He proposed that if we could peer down to a scale of about 10 to the negative 35 meters, the Planck length, the serene geometry of spacetime predicted by general relativity would vanish. In its place, we would find a wildly fluctuating, chaotic landscape. The very concepts of before and after lose their meaning, and the topology of spacetime itself becomes unstable, constantly changing. In this foamy sea, tiny structures, often described as virtual black holes and wormholes, are continuously bubbling into existence from the raw energy of the quantum vacuum, only to annihilate themselves a moment later. These are not the stable structures of science fiction. They are ephemeral fluctuations, appearing and disappearing in time spans so short they are measured in Planck units, the absolute smallest measurements of time possible in our universe. The scale of this activity is almost beyond human comprehension. A typical wormhole in this quantum foam would be about a Planck length in diameter. To put that in perspective, if you scaled a single atom up to the size of our entire observable universe, a Planck length would be roughly the height of a single tree. These wormholes are not just small, they are fundamental. They are not tunnels connecting two distant points in our familiar, large-scale universe. Instead, they represent a fundamental connectivity in the fabric of spacetime itself at the quantum level. They are threads stitching the vacuum together, a dynamic tapestry of bridges and tunnels that exist for mere instants, effectively creating a foam-like structure where the geometry of spacetime is constantly being rewired. This concept isn't just a wild speculation. It forms a crucial bridge in one of physics' greatest quests, the search for a theory of quantum gravity. General relativity beautifully describes the cosmos on a large scale, the warping of spacetime by stars and galaxies. Quantum mechanics, with equal brilliance, describes the world of the very small, the behavior of particles and forces. Yet, the two theories are fundamentally incompatible. They operate under different rules and break down in extreme environments like the center of a black hole or the first moments of the Big Bang. Quantum foam and the miniature wormholes within it is a key feature of several approaches to unifying these two pillars of physics. In some interpretations of loop quantum gravity, for instance, spacetime is not smooth but is composed of discrete, tiny loops and networks, and the foamy, fluctuating nature is a direct consequence of this granular structure. The mini wormholes are like the dynamic connections between these fundamental quanta of space. The implications of this are staggering, even if we can never hope to travel through such a portal. It suggests that what we perceive as the smooth, continuous stage upon which the universe plays out is at its heart a statistical average. The calm spacetime we experience is like the smooth surface of a pond. From a distance, it appears perfectly still and continuous, but up close, you see it's composed of countless, frenetic water molecules constantly jostling and interacting. Our reality emerges from the average behavior of an unimaginably vast number of these quantum gravitational events, including the perpetual birth and death of untold numbers of microscopic wormholes. This perspective transforms the wormhole from a rare and exotic astronomical object into a fundamental, ubiquitous feature of the cosmos, hinting that the connectivity we dream of for interstellar travel is in fact a basic property of the quantum world from which everything arises. While we've been exploring how to build or stabilize wormholes with exotic matter, what if the universe has already done the hard work for us? What if nature itself forged these cosmic shortcuts in the fiery chaos of the Big Bang, leaving behind structures so strange and immense that they could twist the fabric of reality into a tunnel? This brings us to one of the most fascinating and dramatic theories of natural wormhole formation, a theory that involves cosmic strings. Imagine not a string you can tie, but a one-dimensional flaw in the cosmos, an infinitely long, unimaginably dense filament of pure energy thinner than a proton yet possessing the mass of an entire galaxy stretched across light years. These are not just theoretical curiosities, they are hypothetical relics from the universe's first fleeting moments when the fundamental forces of nature were separating from a unified state. As the cosmos cooled and went through a series of phase transitions much like water freezing into ice, cracks and defects might have formed in the fabric of spacetime itself. Cosmic strings are one such possible defect, literal cracks in reality that have persisted for over 13 billion years. The gravitational influence of a cosmic string is as bizarre as its origin. Because it is a one-dimensional object, its gravity warps spacetime in a unique way. While a planet or star creates a gravitational well that pulls objects toward its center in all directions, a cosmic string creates a conical distortion in spacetime. Picture a perfectly flat sheet of paper. Now, if you cut out a narrow wedge and tape the paper back together, the surface becomes conical. That's analogous to the spacetime around a cosmic string. This conical geometry has a startling consequence. It creates a gravitational lensing effect, but more importantly, it opens up the possibility for incredibly exotic topologies. The intense, concentrated mass energy of the string curves spacetime so severely that under the right conditions, two strings interacting or a single string looping back on itself could potentially warp the surrounding space enough to connect two distant regions, effectively forming a wormhole. It's as if the universe itself, under the strain of these primordial defects, pinched spacetime into a tunnel. The specific mechanism often discussed involves the dynamics of two cosmic strings. If two such strings were to move past each other at incredibly high speeds, close to the speed of light, the spacetime curvature around them would become exceptionally complex. Some solutions to the equations of general relativity suggest that the interaction of their gravitational fields could create a closed time-like curve, a time loop, in the space between them. While this is not a stable, traversable wormhole in the traditional sense, it demonstrates the profound power of cosmic strings to manipulate the structure of time and space. In other models, a single cosmic string under immense tension, or a network of interacting strings left over from the early universe, could theoretically provide the necessary framework, the superstructure, upon which a stable wormhole throat could be formed. The string's immense energy density could act as a natural source of the exotic matter or the negative pressure needed to keep the throat from collapsing, a ready-made component from the dawn of time. Considering the sheer scale of these objects highlights both the promise and the profound challenges of this theory. A typical cosmic string might have a mass energy density of about 10 million billion tons for every centimeter of its length. The gravitational forces involved are almost beyond comprehension. A spaceship approaching one wouldn't just be pulled inward. The conical spacetime around it would create a double image of the sky, and passing a string could, in theory, transport you to another part of the universe instantaneously without you even feeling acceleration, a phenomenon tied to the global topology of the conical space. However, the sheer violence of these environments makes the idea of a controlled, stable wormhole formed from strings highly speculative. The energies are so extreme that they might only create unstable portals or structures that are topological curiosities rather than practical passageways. Furthermore, despite decades of searching, astronomers have not yet found definitive evidence for cosmic strings. They remain a beautiful and powerful prediction of certain grand unified theories in particle physics, but one that still awaits confirmation. Their potential role in wormhole formation stands as a testament to the deep and often unexpected connections between the very large and the very small, suggesting that the keys to interstellar travel might be hidden in the earliest moments of cosmic history. But if we want to find a wormhole that nature might have already built, we don't necessarily need to look for cosmic strings. The cosmos might be hiding these gateways in plain sight, concealed within the most terrifying and enigmatic objects we know, black holes. This leads us to a theory that radically reimagines the final destination of a black hole, suggesting that the point of no return might not be an end at all, but a beginning. To understand this, we have to move beyond the simplest model of a black hole. The Schwarzschild black hole, the one we typically picture, is perfectly spherical and static. It possesses a crushing central singularity, a point of infinite density, and the event horizon from which nothing can escape. It's a cosmic dead end. However, most things in the universe spin, and black holes are no exception. When we account for rotation, we get a much more complex and fascinating object described by the Kerr metric, a solution to Einstein's equations discovered by physicist Roy Kerr in the 1960s. The Kerr black hole isn't a simple pit, it's a dynamic, whirling vortex in spacetime, and its internal structure is where the magic happens. The anatomy of a rotating Kerr black hole is profoundly different from its static cousin. Instead of a single, inescapable event horizon, it has two. The outer event horizon is similar to the one we know, the boundary beyond which escape is impossible. But inside that, there is a second boundary called the inner horizon or the Cauchy horizon. This inner horizon is a region of extreme, theoretically infinite blue shifting, where any radiation or energy falling into the black hole gets concentrated into a devastating surge. But between these two horizons lies a region known as the ergosphere, an oblate spheroid where spacetime itself is dragged around the black hole at incredible speeds, a phenomenon called frame dragging. It's as if the black hole is twisting the fabric of the universe around it like a whirlpool. The most mind-bending feature, however, lies at the very center. Instead of a point singularity, the Kerr solution predicts a ring singularity. Imagine all the mass of the black hole not crushed into a single point, but spun out into a thin, rotating ring. This isn't a solid ring you could touch. It's a one-dimensional loop of infinite density, a flaw in spacetime geometry. This ring singularity is the key to its potential as a portal. The equations describing the interior of a Kerr black hole suggest something extraordinary. If you were to approach this ring singularity on a trajectory that is precisely aligned with its axis of rotation, you might not be crushed into oblivion. The unique geometry of the rotating ring could, in theory, provide a path through it. The mathematics indicates that the spacetime curvature inside the Kerr black hole could connect to another region of spacetime, potentially a different universe or a distant part of our own. It would function as a wormhole, an Einstein-Rosen bridge built by nature's most violent gravitational engines. You wouldn't navigate this tunnel with a spaceship's controls. You would be hurled through it by the very forces that tear apart a standard black hole, a chaotic and unpredictable transit through the ring. Now, the monumental challenge, and the reason this remains a highly speculative theory, lies in the journey itself. To even reach the ring's singularity, any object would have to survive passage through the inner horizon. This Koch horizon is notoriously unstable, as matter and radiation from the entire lifetime of the black hole pile up at this boundary. They create a wall of infinite energy density, often called a blue sheet or a mass inflation singularity. It's a region of such extreme physical conditions that any complex structure, from an atom to a spacecraft, would be utterly obliterated by an intense blast of radiation long before it got near the central ring. Furthermore, the tidal forces, the difference in gravity between your head and your feet, would still be fearsomely strong, likely stretching any object into a stream of particles in a process known as spaghettification. So, while the ring singularity offers a tantalizing mathematical exit, the physical environment surrounding it appears to be unsurvivable, acting as a brutal, one-way filter that destroys anything trying to pass. The implications of this theory stretch the imagination. If a Kerr black hole does contain a traversable wormhole at its heart, then every rotating black hole scattered across the galaxy could be a gateway, not a grave. This introduces the breathtaking concept of a white hole on the other side. A white hole is the theoretical time reversal of a black hole. Instead of everything falling in, everything is spewed out. Matter and energy that enters the black hole in our universe might be violently ejected from a white hole into another universe or another time. Our universe's black holes could be the white holes of another cosmos, and vice versa, creating an eternal cycle of matter and energy flowing between different realities. This paints a picture of a multiverse intricately connected by these gravitational tunnels, with each black hole berth potentially signaling a new universe being forged on the other side. While the practicalities of survival make it an improbable method for travel, the Kerr wormhole theory forces us to reconsider the ultimate fate of matter and the very architecture of reality, suggesting that the most destructive objects in the cosmos might also be its most creative. Moving from the immense gravitational whirlpools of black holes, we encounter a theory that ties together two of the most profound puzzles in modern cosmology. What if the very substance that makes up the vast majority of the universe's mass is also the key to holding these cosmic tunnels open? This speculative idea proposes a deep connection between wormholes and dark matter, suggesting that the invisible scaffold of the cosmos might be woven from the same fabric needed for interstellar shortcuts. We know that roughly 27% of the universe is made of dark matter, a mysterious substance that doesn't emit, absorb, or reflect light, yet its gravitational pull is the only thing keeping galaxies from flying apart. Then there's dark energy, making up about 68% of the cosmos, which is driving the accelerated expansion of the universe. Both are completely invisible to our telescopes, detectable only through their gravitational effects on the things we can see. The remaining 5% is everything else, all the stars, planets, gas, and dust that constitute the familiar, observable world. The audacious proposal here is that the 95% of the universe we don't understand might be intrinsically linked to the existence and stability of wormholes. To see how this could work, let's revisit the critical problem of wormhole stability. As we've discussed, a traversable wormhole requires exotic matter, a substance with negative energy density or negative pressure, to act as a counter-gravitational force, propping the throat open against its own tendency to collapse. For decades, physicists have searched for a plausible source of this exotic matter, often looking to quantum effects like the Casimir vacuum. But what if the answer isn't in the tiny quantum realm, but is instead spread diffusely across the entire cosmos? Dark energy, with its repulsive gravitational effect, is the most obvious candidate. Its negative pressure is exactly what's causing the expansion of the universe to speed up, and mathematically, this negative pressure is precisely the kind of quality that exotic matter possesses. If we could somehow find a way to concentrate or manipulate dark energy, to funnel it into the throat of a wormhole rather than letting it push all of space apart, it could theoretically provide the stabilizing force needed to make the wormhole traversable. The challenge, of course, is that dark energy appears to be a uniform property of the vacuum of space itself. It's incredibly weak at local scales but dominates on cosmic scales due to its sheer omnipresence. Harnessing it would mean learning to manipulate the vacuum energy of the universe on a grand scale, a feat far beyond our current comprehension. Dark matter offers another tantalizing possibility. We know it interacts gravitationally, but it doesn't seem to interact via the electromagnetic force, which is why it's invisible and passes right through normal matter. Some theoretical models propose that dark matter could be made of particles we haven't yet discovered, such as actions or weakly interacting massive particles known as WIMP. Now, certain speculative extensions to the standard model of particle physics suggest that some of these hypothetical dark matter particles could have very unusual properties. What if some component of the dark matter halo surrounding our galaxy isn't just made of one type of particle, but includes a fraction of particles that naturally exhibit negative energy density under certain conditions? If that were the case, then the exotic matter needed to line a wormhole's throat might not be a rare, lab-engineered substance, but a natural resource that's been floating around us all along. We just need to learn how to gather and shape it. This transforms the problem from one of pure creation to one of cosmic harvesting, a concept that sounds like science fiction but is grounded in the real mystery of what dark matter actually is. Imagine a future where our galaxy is not just a collection of stars, but a network of natural transit systems. The dark matter halos that envelop galaxies like our Milky Way could be littered with primordial wormholes formed in the Big Bang, their throats lined and stabilized by the very dark matter that makes up the halo. These wouldn't be artificial constructions, but natural geological features of the cosmos, as inherent to the universe as black holes or neutron stars. A spacecraft wouldn't need to generate its own exotic matter. It would simply need to navigate to one of these stable, naturally occurring gateways, using our understanding of dark matter's gravitational influence as a map. This idea elegantly weaves together two mysteries, suggesting that the reason we haven't found a definitive signature of dark matter particles in our underground detectors on Earth is because we're looking for the wrong signals. Perhaps their most dramatic effect isn't at the particle level in a lab, but on the grand cosmological scale, where they serve as the invisible architects of the universe's connective tissue. Of course, this remains a highly speculative theory, but it's a powerful example of how solving one cosmic enigma could unexpectedly unlock the secrets to another. The ongoing quest to detect and understand dark matter and dark energy isn't just about completing our inventory of the universe's contents. It might be the first step toward realizing that the universe has already provided the infrastructure for our greatest adventures. The invisible 85% of reality might be the very thing that makes the cosmos navigable, hiding the threads that connect the stars in plain sight. Building on this idea of a deeply interconnected cosmos, we arrive at one of the most profound and revolutionary theories to emerge in theoretical physics in recent years, a concept that boldly bridges the gap between the universe's largest structures and its smallest particles. This is the ER=EPR conjecture, a proposal that suggests the bizarre phenomenon of quantum entanglement and the cosmic structure of wormholes are not just analogous, but might be two different descriptions of the very same thing. To grasp the sheer audacity of this idea, we first need to revisit its two components. ER stands for the Einstein-Rosen bridge, the original wormhole born from the equations of general relativity. EPR, on the other hand, stands for Einstein, Podolsky, and Rosen, who in 1935 published a famous paper highlighting what they saw as a deeply troubling, spooky action at a distance in quantum mechanics, a phenomenon we now call quantum entanglement. Quantum entanglement is a cornerstone of quantum mechanics that even Einstein found difficult to accept. It occurs when two particles, say a pair of electrons or photons, are created or interact in such a way that their properties become inextricably linked. From that moment on, no matter how far apart they are separated, whether by a millimeter or by a million light years, they remain a single, connected quantum system. Measure the spin of one entangled particle here on Earth, and you instantly know the spin of its partner in a distant galaxy. This connection appears to operate faster than the speed of light, a notion that violated Einstein's understanding of relativity and led him to dismiss it as spooky. For decades, these two pillars of physics, general relativity and quantum mechanics, stood apart. One described the force of gravity and the geometry of space-time. The other described the probabilistic behavior of particles and forces. They seemed to operate under entirely different rules, and physicists struggled to find a common language between them. The ER equals EPR conjecture, largely championed by physicists like Juan Maldacena and Leonard Susskind, proposes that this common language has been hiding in plain sight. The conjecture posits that the spooky connection between two entangled particles, an EPR pair, is physically mediated by a tiny, non-traversable Einstein-Rosen bridge, a microscopic wormhole. In this view, entanglement doesn't involve any mysterious, invisible signal flying between the particles. Instead, the particles are connected because they are literally the two mouths of a single, incredibly small wormhole. The correlation between them is a geometric connection in the fabric of spacetime itself, a ghostly thread woven from the universe's underlying structure. This radically reframes entanglement not as a weird quantum correlation, but as a tangible, geometric bridge, effectively turning the entire quantum world into a vast, intricate network of Planck-scale wormholes. Think of it this way: we usually visualize two entangled particles as separate dots with an invisible line between them. The ER equals EPR conjecture suggests that this picture is a flawed classical simplification. A more accurate, albeit mind-bending, image is that the two particles aren't distinct points sitting in empty space at all. They are the only visible parts of a single, deeper structure, the two ends of a submicroscopic tunnel. The connection isn't a line drawn through space, it is a shortcut in spacetime. This elegantly resolves the spooky action problem. No information is actually traveling faster than light between the two particles because, from a geometric perspective, they aren't truly far apart. The wormhole provides an ultra-short path connecting them, making their instantaneous correlation a natural consequence of spacetime geometry rather than a mysterious violation of cosmic speed limits. The implications of this idea ripple out to touch upon one of physics' most vexing problems: the black hole information paradox. This paradox asks what happens to the information about an object, all the data specifying its atomic structure and properties, when it falls into a black hole. According to quantum mechanics, information can never be truly destroyed. But according to classical general relativity, that information is lost forever behind the event horizon, seemingly violating a core quantum rule. The ER equals EPR conjecture offers a beautiful geometric solution. Imagine two entangled particles. One falls into a black hole while the other remains outside. According to the conjecture, these two particles are connected by a microscopic wormhole. When the infalling particle carries its information across the event horizon, that information isn't lost. It can, in principle, travel through the wormhole bridge and be preserved in the correlations of the Hawking radiation emitted by the black hole. The wormhole acts as a hidden channel, ensuring that information is never truly lost but merely transferred, thus preserving the laws of quantum mechanics even in the face of a black hole's immense gravity. This perspective suggests a startling new vision of reality. The empty space around us, the quantum vacuum, might not be a barren void. If every pair of entangled particles is connected by a tiny wormhole, then the vacuum is in fact a densely woven fabric of these microscopic bridges, a space-time entanglement network. This provides a potential physical mechanism for the quantum foam we discussed earlier. The frenetic bubbling of virtual particles could be seen as the constant formation and disappearance of these ephemeral wormholes, weaving the very fabric of space-time from the bottom up. It hints that space-time itself may not be a fundamental stage, but an emergent property that arises from a vast, underlying network of quantum entanglement. In other words, the connectivity of space and the flow of time as we experience them might be a direct consequence of countless trillions of entangled particles linked by an unimaginably complex web of Planck-scale bridges. This concept of a black hole's interior potentially hiding a gateway naturally leads us to another incredible and highly speculative piece of the cosmic puzzle: the idea that every black hole entrance could be permanently paired with a white hole exit. If a black hole is the universe's ultimate one-way street, a place where anything can fall in but nothing can ever escape, then a white hole is its perfect theoretical opposite. Imagine a cosmic geyser, a region of space-time where matter and energy can only pour outward, and nothing, not even light, can ever cross inward. It is the ultimate exit-only zone, a fountain of existence that refuses to take anything back. The symmetry between these two objects is mathematically beautiful. In fact, if you were to take the equations for a Schwarzschild black hole and literally reverse the direction of time in them, you would get the mathematical description of a white hole. This time reversal symmetry suggests that if black holes exist, then white holes should, in principle, be just as possible within the framework of general relativity. Yet, despite this elegant mathematical symmetry, white holes present a profound physical paradox that makes many physicists deeply skeptical of their actual existence. Think about how a white hole would have to behave. It would spontaneously and continuously eject matter and energy that had fallen into its linked black hole, but it would be completely impervious to any influence from the outside universe. No external force could alter it, no object could enter it, and no signal could penetrate its boundary. This creates a serious problem with causality, the fundamental principle that cause must always precede effect. Where did all this ejected matter and energy originally come from? In the most straightforward wormhole model, it would be the material that fell into the connected black hole. But a white hole, by its very definition, has no past from the perspective of our universe. It simply appears fully formed and begins spewing out material with no prior history that we can observe or interact with. This makes it seem like an effect in search of a cause, a cosmic violation of the narrative flow of time as we understand it. Consider the life cycle of such an object. If a white hole were to form, how would it even begin? It couldn't be born from the gravitational collapse of a star, as that process creates a black hole. It would have to simply pop into existence, already containing a vast amount of mass and energy, and immediately begin expelling it. From our perspective in the external universe, this would look like a sudden, inexplicable eruption of matter and radiation from a point in space, defying all known laws of thermodynamics that govern how order and disorder evolve. The sudden appearance of a massive, ordered object from nothing would seem to be a decrease in entropy, flying in the face of the second law of thermodynamics, which states that the total disorder in a closed system like the universe can only stay the same or increase over time. This is a major reason why white holes are considered thermodynamically forbidden by many. They appear to be cosmic miracles that create order out of nothing, rather than natural endpoints of physical processes. So, if white holes are so problematic, why does the idea persist? their greatest appeal lies in their potential role as the other end of a wormhole. In this complete picture, you don't have a lonely black hole or a mysterious white hole in isolation. Instead, you have an Einstein-Rosen bridge that seamlessly connects the two. The black hole is the entrance, the white hole is the exit, and the wormhole is the tunnel in between. Matter that crosses the event horizon of the black hole in our universe would, after a journey through the wormhole, however turbulent and destructive, be ejected from the white hole into another region of spacetime. This other region could be a distant part of our own universe, or it could be an entirely separate universe altogether. This model provides a potential origin story for the white hole's ejected material. It's not magically created, it's just being transferred from the black hole's inventory. This solves the causality problem from a global, multi-universe perspective, even if it remains completely inaccessible and unverifiable from our local vantage point. This leads to one of the most breathtaking speculative concepts in all of cosmology, that our entire universe might have been born from a white hole in a parent cosmos. Imagine a massive star in another pre-existing universe collapsing to form a black hole. From the perspective of observers in that universe, it's a grim finale. But according to this theory, the interior of that black hole, through the mechanism of a wormhole, connects to a white hole eruption in a new baby universe. The Big Bang that created our cosmos could, in this stunning scenario, be viewed as the violent white hole output of a black hole formed in a different reality. This provides a potentially endless cycle of cosmic genesis, a multiverse where every black hole death gives birth to a new universe, each with its own fundamental constants and physical laws. While this remains a highly speculative and untestable hypothesis, it offers a poetic and grand vision of cosmic evolution, where the most destructive events in one realm become the creative seeds for another, forever weaving the fabric of existence across countless realities. We've looked at wormholes born from black holes and cosmic strings, but what if the most common wormholes aren't forged in the violence of stellar collapse, but are instead ancient relics from the very birth of everything? This theory takes us back to the ultimate beginning, to a fraction of a second after the Big Bang, when the entire cosmos was a seething, impossibly dense and energetic soup. In that primordial furnace, the very fabric of spacetime was undergoing violent quantum-scale fluctuations. It was an era of cosmic chaos where the laws of physics as we know them were being written in real time. Within that maelstrom, the theory suggests, the intense pressures and energies could have twisted spacetime into knots, pinching it into tiny tunnels, primordial wormholes. These wouldn't be the carefully constructed bridges of a future civilization, but rather natural geological features of the cosmos, as fundamental as the cosmic microwave background radiation. The survival of such a structure is a story in itself. In the first fleeting moments, countless numbers of these wormholes would have formed, but most would have instantly collapsed, disappearing back into the quantum foam from which they came. However, some models suggest that a fraction of them could have been stabilized and inflated along with the rest of the universe. How? One possibility is that they were threaded by cosmic strings, those one-dimensional defects from the early universe we discussed earlier, which could have acted as a reinforcing scaffold. Another, even more exotic idea involves the rapid expansion of the universe during the period of inflation. As space itself stretched at an exponential rate, it's conceivable that some of these nascent wormholes were caught in the expansion, their throats stretched and frozen into a stable configuration before they had a chance to collapse. They would have been woven into the expanding fabric of the cosmos, relics of a time when the universe was less than a second old. So, if these ancient gateways are scattered throughout space, how would we ever find one? We can't just point a telescope and see a glowing portal. The most promising method relies on a phenomenon we already use to study the universe: gravitational lensing. As you'll recall, any massive object warps the fabric of spacetime around it, bending the path of light that passes nearby. a wormhole, despite potentially having a relatively small physical throat, would still possess a significant gravitational field. If one were to pass between us and a distant star or galaxy, it would act as a gravitational lens, distorting and magnifying the light from that background object. But here's the crucial distinction: the lensing signature of a wormhole would be unique. Unlike a black hole, which creates a single, distorted ring of light known as an Einstein ring, a wormhole's unique geometry could theoretically create a double image. Because a wormhole has two mouths connected by a tunnel, light can travel to us along two different paths, one around the mouth closest to us, and another that actually passes through the wormhole itself and emerges from the other mouth. This could create a distinctive, paired set of images or an anomalous pattern in the lensed light that doesn't match the profile of a simple black hole or a dark matter clump. Astronomers are already sifting through data from telescopes like the Hubble and the James Webb Space Telescope, looking for these subtle gravitational anomalies. They're analyzing the light from millions of distant quasars and galaxies, searching for the telltale, fleeting brightening and distortion that could betray the presence of a hidden, massive object. A primordial wormhole drifting silently through the galactic halo would be a perfect candidate. Finding one would be a monumental discovery, not just confirming a prediction of general relativity, but opening a window into the universe's most violent and mysterious first moments. It would mean that our cosmos is not just expanding, but is also intricately connected by a hidden network of tunnels, a fossil record of creation itself waiting to be mapped. Now let's consider an even more extreme form of cosmic fuel, a hypothetical substance so potent and so bizarre that it could theoretically prop open a wormhole with ease, but at a potentially catastrophic cost. This brings us to the theory of wormhole stabilization using phantom energy. You'll recall that dark energy is the mysterious force accelerating the expansion of our universe, characterized by a powerful negative pressure. Phantom energy is a specific and highly speculative subset of dark energy. What sets it apart is the equation of state, a key parameter in cosmology that describes the relationship between the pressure and density of a substance. For phantom energy, this value is less than -1, meaning its negative pressure is even stronger than that of the quintessence models usually associated with dark energy. This isn't just a gentle repulsive force, it's a violently anti-gravitational push. If exotic matter is the material needed to line a wormhole's throat to keep it from collapsing, then phantom energy would be that material on steroids. Its intense negative pressure would generate a tremendous repulsive gravitational effect, more than sufficient to counteract the natural tendency of the wormhole's throat to pinch shut. In fact, the theoretical models suggest that phantom energy wouldn't just stabilize the wormhole, it would aggressively force it open. You can picture this as inflating a balloon with an ultra-high pressure pump. The phantom energy would act as that pump, powerfully expanding the tunnel and creating a wide, stable passageway far more effectively than the minuscule negative energy from the Casimir effect ever could. For a moment, this appears to be the ultimate solution, a ready-made, universe-spanning substance that could transform wormhole engineering from a quantum-scale puzzle into a grand cosmological endeavor. However, this incredible power comes with a terrifying and inherent instability. The very property that makes phantom energy so effective at holding the wormhole open is also its fundamental flaw. The defining characteristic of phantom energy is that its energy density increases as the universe expands. This is the opposite of all other known forms of matter and energy, which become more diffuse and less dense as space stretches. Because phantom energy grows stronger over time, it leads to a theoretical future for the cosmos called the Big Rip. In this apocalyptic scenario, the repulsive force of phantom energy would eventually overcome all other forces in the universe, first tearing apart galaxy clusters, then galaxies themselves, then stars from their planetary systems, then planets, and finally, ripping apart atoms and the very fabric of space-time in the final moments. Now apply this destructive nature to the confined, delicate structure of a wormhole. If you were to line a wormhole's throat with phantom energy, you are essentially introducing this self-amplifying, destructive force directly into its architecture. While it would successfully hold the throat open initially, the phantom energy would not remain stable. Its density would begin to increase within the wormhole's structure. This wouldn't be a slow process. The intense curvature and confined space of the wormhole throat could accelerate the instability. The ever-increasing negative pressure would put more and more stress on the space-time fabric of the tunnel itself. Instead of providing a steady reinforcement, the phantom energy would act like a corrosive, expanding force that the wormhole's structure cannot indefinitely contain. The inevitable result would be a catastrophic failure, a sort of wormhole supernova. The phantom energy would eventually cause the wormhole to rupture, violently tearing the space-time tunnel apart from the inside out. This wouldn't just be a collapse into a singularity, it would be a full-blown disintegration of the wormhole structure. The event would likely release an immense amount of energy, a burst of gravitational waves and radiation signaling the destruction of the cosmic shortcut. Therefore, using phantom energy represents a profound trade-off. It offers a theoretically potent mechanism for creating a traversable wormhole, but it fundamentally constructs that wormhole as a temporary and inherently unstable entity, one doomed to a spectacular and violent end. It transforms the wormhole from a permanent bridge into a fleeting, brilliant, and ultimately self-destructive flare in the cosmos. We've been exploring how wormholes might link different parts of our own cosmos, but what if their true potential is far grander? What if these space-time tunnels don't just offer shortcuts across our universe, but serve as gateways to entirely different universes altogether? This brings us to the breathtaking multiverse gateway theory, an idea that places wormholes at the heart of one of the most provocative concepts in modern physics, the multiverse. Within this framework, a wormhole could be more than an interstellar bridge. It could be a literal doorway into another reality, with its own unique history, physical laws, and perhaps even entirely different forms of matter and energy. To understand how this could happen, we need to revisit the very early universe and the theory of cosmic inflation. This theory posits that a fraction of a second after the Big Bang, the fabric of space itself underwent an exponential, faster-than-light expansion, smoothing and flattening our observable universe into the relatively uniform cosmos we see today. But a compelling extension of this idea, known as eternal inflation, suggests that this explosive expansion didn't happen just once in one place. Instead, the inflationary process could be ongoing, a kind of cosmic chain reaction where some regions of space stop inflating to form pocket universes like our own, while the space between them continues to inflate eternally. Our entire cosmos, with its hundreds of billions of galaxies, might be just one bubble in a vast, ever-growing cosmic foam of universes. Normally, these bubble universes are completely causally disconnected from one another, forever separated by expanding walls of inflating space. But what if a wormhole, a topological feature of spacetime, could form a stable connection through that inflating barrier, linking the interior of our bubble to the interior of another? In this view, a traversable wormhole could be the one structure capable of piercing the isolation of these parallel worlds, making the multiverse navigable. String theory, a leading candidate for a theory of everything, adds even more depth and possibility to this picture. One of the most striking implications of string theory is the existence of a vast landscape of possible vacuum states. Each of these states corresponds to a different configuration of the extra dimensions string theory requires, and each configuration determines the fundamental constants of physics. Things like the strength of gravity, the mass of the electron, or the number of dimensions we perceive. In this landscape, our universe is just one specific valley with a particular set of constants that made life possible. Countless other valleys, other universes, exist with wildly different laws. Some might have stronger nuclear forces where only giant atoms can exist. Others might have gravity so weak that no stars ever form, and still others might have more than 3 spatial dimensions. The multiverse gateway theory suggests that the 2 mouths of a wormhole could, through some profound quantum gravitational process, become anchored in 2 different valleys of this landscape. One mouth would reside in our universe, and the other would open into a universe with a completely different set of physical rules. Imagine stepping through such a gateway. The journey through the wormhole's throat would have to provide a protected environment, a kind of transition zone where the physics gradually shifts from one set of laws to the other. This would be absolutely essential because if the transition were instantaneous, the very atoms that make up your body might not be stable under the new rules. The nuclear forces that hold your atomic nuclei together, or the electromagnetic forces that govern chemistry, could be fundamentally different on the other side. A traversable multiversal wormhole would need to be lined with exotic matter that not only holds the geometry open but also somehow mediates this physics transition, preventing you and your ship from disassembling into a cloud of fundamental particles the moment you cross the boundary. The engineering challenges here are, of course, unimaginable, but the theoretical possibility paints a picture of a cosmos of almost infinite variety, where wormholes act as the ultimate conduits of exploration. This concept also offers a potential resolution to one of the great mysteries of our own universe, why its physical constants appear to be so finely tuned for the existence of life. If ours is just one among a nearly infinite number of universes in the multiverse, each with random constants, then it's no surprise we find ourselves in one of the rare ones that can support complex structures like stars, planets, and biologists. We are simply the product of a cosmic selection effect. The multiverse gateway theory gives this abstract idea a potential physical mechanism. We wouldn't just be a random, isolated bubble. We could, in principle, be connected to our sibling universes. A sufficiently advanced civilization might not just gaze at other universes from afar, but could potentially send probes through these wormhole bridges to directly sample the incredible diversity of cosmic environments, turning the philosophical concept of the multiverse into a tangible, physical frontier. The wormhole, therefore, transforms from a mere transportation device into the ultimate scientific instrument, a window into the deepest architecture of reality. At the heart of the wormhole puzzle lies a deep and fundamental schism in our understanding of physics, a divide that only a complete theory of quantum gravity can hope to bridge. For over a century, we have lived with 2 incredibly successful but seemingly incompatible descriptions of reality. On one hand, we have Einstein's general relativity, which paints a beautiful geometric picture of the cosmos. It describes gravity not as a force but as the elegant curvature of spacetime itself, a smooth, continuous fabric warped by mass and energy. This theory masterfully explains the orbits of planets, the bending of light around galaxies, and the very expansion of the universe. On the other hand, we have quantum mechanics, the rulebook for the subatomic world. It governs the behavior of particles and forces with astonishing precision, but it describes a reality that is fuzzy, probabilistic, and fundamentally granular. In the quantum realm, particles can be in 2 places at once, and empty space is a seething foam of virtual particles. The problem is that these 2 theories speak different languages. General relativity is a classical theory of smooth, deterministic geometry, while quantum mechanics is a probabilistic theory of discrete, quantized fields. When their domains collide, in the heart of a black hole or at the very first instant of the Big Bang, the equations of both theories break down, yielding nonsensical answers like infinities. To truly understand a wormhole, a structure that is both a macroscopic feature of spacetime geometry and likely subject to the wild fluctuations of the quantum world, we need a framework that unifies these two pillars of physics. We need a theory of quantum gravity, a set of laws that describes how spacetime itself behaves at the smallest possible scales. Two of the most prominent candidates in the quest for quantum gravity are string theory and loop quantum gravity, each offering a radically different vision of reality's foundation. String theory proposes that the fundamental constituents of the universe are not point-like particles, but incredibly tiny, vibrating strings or membranes. What we perceive as different particles, electrons, quarks, photons, are actually just different vibrational modes of these underlying strings, much like different musical notes played on a single guitar string. One of string theory's most profound implications is that it requires extra dimensions of space beyond the three we experience. For the math to work consistently, these strings must vibrate in a 10 or 11-dimensional reality. The reason we don't perceive these extra dimensions is that they are compactified, or curled up into a space so infinitesimally small that they are hidden from our view. This theory naturally includes gravity with the graviton, the hypothetical particle that mediates the gravitational force, emerging as a specific vibrational state of a closed string. From a wormhole perspective, string theory's landscape of possible vacuum states, each corresponding to a different way of curling up the extra dimensions, provides a vast canvas for wormholes to connect not just different points in space, but entirely different universes with different physical laws. The vibrational properties of strings could also be key to understanding the stability of a wormhole's throat, potentially offering a mechanism to prevent its catastrophic collapse. Loop quantum gravity, in contrast, takes a more direct approach by quantizing spacetime itself. Instead of postulating new fundamental objects, it seeks to rewrite general relativity in the language of quantum mechanics. In this theory, space is not a smooth, continuous background. It is composed of tiny, discrete, indivisible quantum-minimal units of volume. Picture the fabric of reality not as a smooth sheet, but as a vast, dynamic network of interconnected loops, like an unimaginably fine mesh. The links of this network represent the smallest possible areas, and the nodes represent the smallest possible volumes. The theory gets its name from these fundamental loops of gravitational field that weave the network of space. In this granular picture, the geometry of spacetime is derived from the way these loops connect and interact. This has a direct and stunning implication for wormholes. The quantum foam we discussed earlier isn't just a vague metaphor in loop quantum gravity. It is the literal foundation of reality. The constant fluctuations in this spin network could naturally give rise to wormholes as topological features, connections where the network forms a non-trivial loop, essentially creating a microscopic bridge between two otherwise distant nodes in the spatial fabric. A traversable wormhole, then, might be a stabilized, macroscopic version of this fundamental connectivity, a structure where a vast number of these quantum loops have been coaxed into forming a coherent tunnel. So, how would these theories change our view of a wormhole's formation and stability? In the context of general relativity alone, creating a wormhole seems to require a Herculean effort, finding or manufacturing exotic matter in astronomical quantities. But in a theory of quantum gravity, the very question might be reframed. Wormholes might not be something we build from the top down, but rather something we cultivate or enlarge from the bottom up. Since both string theory and loop quantum gravity suggest that spacetime has a fundamental granularity at the Planck scale, they imply that microscopic wormholes are a natural and ubiquitous part of the quantum vacuum. The challenge for a future civilization wouldn't be to create a wormhole from nothing, but to find a way to isolate and inflate a pre-existing Planck-scale wormhole, stabilizing it against collapse and enlarging its throat to a usable size. This is a fundamentally different engineering paradigm. It would be akin to finding a microscopic seed in the soil of space-time and nurturing it into a mighty tree, rather than trying to construct the tree from lumber and nails. The behavior of matter and energy traversing a wormhole would also be dramatically different when viewed through the lens of quantum gravity. The classic problem of spaghettification, where tidal forces stretch an object into a stream of particles, might be mitigated or completely transformed. In a quantized spacetime, there is a limit to how small distances can become, which could prevent the tidal forces from becoming truly infinite. The journey through the wormhole's throat might not be a smooth glide through warped space, but a quantum walk across the nodes of the spin network in loop quantum gravity, or a passage guided by the interactions of strings and branes in string theory. Information loss, the great paradox of black holes, is also directly addressed by these frameworks. The ER equals EPR conjecture, which posits that entangled particles are connected by tiny wormholes, finds a natural home in string theory, where the geometry of spacetime and quantum entanglement are two sides of the same coin. This suggests that the wormhole itself could act as a protective conduit for information, ensuring that anything that enters one mouth has a perfectly correlated path to exit the other, preserving the laws of quantum mechanics. Ultimately, the pursuit of a theory of quantum gravity is not just an academic exercise. It is the essential key to unlocking the deepest secrets of wormholes. Without it, our understanding is like trying to describe a snowflake using only the physics of water waves, missing the intricate crystalline structure that arises from its molecular nature. String theory and loop quantum gravity, for all their mathematical complexity, represent our best efforts to peer into that deeper structure of reality. They suggest a universe where wormholes are not rare anomalies, but fundamental expressions of a spacetime that is, at its heart, quantum, connected, and born from a network of relationships. Discovering the correct theory will not only tell us if wormholes can exist, but it will reveal what they truly are, whether they are vibrating strings woven into a bridge, a solidified loop in the fabric of space, or something even more marvelous that we have not yet dared to imagine. This brings us to a fascinating and elegant resolution to all those troubling time travel paradoxes, a concept that doesn't forbid time travel outright, but instead imposes a kind of cosmic censorship on chaos. The Novikov self-consistency principle, proposed by the Russian physicist Igor Novikov, offers a compelling answer to the grandfather paradox. It simply asserts that if time travel to the past is possible, then the timeline must be a single, immutable, and self-consistent loop. Any actions you take while in the past were always a part of that past. You cannot change history because your very presence and actions in the past are what created the history you already know. The principle argues that the laws of physics themselves would conspire to prevent any inconsistencies from ever occurring, making paradoxes physically impossible. Apply this to our wormhole time machine scenario. You step through the exit that leads 9 years into the past, armed with the intention of preventing some long-ago disaster. The Novikov principle suggests that you will fail not because of a lack of effort, but because the universe is a closed, consistent system. Your attempt to change the past is part of the unchangeable chain of events. Perhaps you try to deliver a warning, but a sudden noise distracts the recipient at the crucial moment. Maybe you attempt to disable a critical piece of machinery, only to find that your actions inadvertently cause a minor malfunction that, days later, leads someone else to perform better maintenance, ultimately ensuring the machine works perfectly when it is needed. In every conceivable scenario, your actions in the past loop back to guarantee the very outcome you are trying to prevent. You were never a foreign element intruding on history. You are always a hidden gear in the clockwork, your journey and your efforts an integral, preordained part of the events that unfolded. This transforms the nature of free will in a time travel context. It's not that you lack free will, you are free to make any choice you wish. However, the Novikov principle dictates that your choices in the past will always be exactly those that lead to the future from which you came. You choose to go back in time, and you choose to take certain actions, but those choices were predetermined by the consistency of the timeline. It's a profound and somewhat dizzying concept. Your future self's journey into the past is the cause of events that motivate your younger self to eventually become that future time traveler in the first place. The loop has no true beginning or end. It just is a perfectly self-contained and consistent story where every event reinforces every other event. Within the framework of a wormhole, this principle suggests a remarkable stability. Unlike Stephen Hawking's chronology protection conjecture, which posits that quantum feedback would violently destroy a time machine, the Novikov principle implies that the wormhole would remain open and functional. The universe wouldn't need to destroy the time machine because the timeline it enables is already paradox-free. The wormhole becomes a stable feature of space-time, not as a tool for rewriting history, but as a window into a past that is as fixed and unchangeable as a recording. Looking through the wormhole, you wouldn't see a past you could alter. You would see a past that already includes your own future observations. This turns the wormhole from a potential instrument of chaos into a device for perfect historical observation, a means to witness the immutable tapestry of cause and effect in its full, interconnected glory. The implications stretch far beyond simple paradox avoidance. If the Novikov principle is correct, then the entire history of the universe, from the Big Bang to the distant future, is a single monolithic block. Every wormhole time journey that will ever happen has already happened and is woven into the fabric of that history. This introduces a deeply deterministic view of reality, where the future is as fixed as the past. For a hypothetical civilization that mastered wormhole time travel, history would not be a mystery. They could, in theory, send observers back to any era to document events with perfect accuracy, creating a complete and unalterable record of everything that ever was. The very existence of their time travel technology would be proof that the universe operates on a foundation of absolute self-consistency, where every event, no matter how small, is locked into a perfect, unbreakable harmony with every other. Shifting our perspective from strings and loops to an even more radical view of reality, we encounter a theory that suggests the very three-dimensional universe we inhabit might be a grand illusion, a cosmic projection. This is the holographic principle, and its connection to wormholes reveals a universe that is fundamentally interconnected in ways that defy our classical intuition. The principle itself originates from the study of black holes. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that a black hole's entropy, a measure of its information content, is not proportional to its volume as you might expect, but to the surface area of its event horizon. This was a profound clue. In everyday systems, the amount of information something can contain scales with its volume. Think of a hard drive. Its capacity is determined by the three-dimensional space inside it where you can store bits. But a black hole, the ultimate information storage device, seemed to be telling us that all the information about everything that ever fell into it was somehow encoded on its two-dimensional surface, like a complex movie stored on a flat DVD. The holographic principle takes this stunning insight and applies it to the entire universe. It proposes that our reality, with all its three spatial dimensions of height, width, and depth, along with time, is actually a projection from a two-dimensional surface at the very boundary of the cosmos. We are, in a very real sense, living inside a hologram where the true, fundamental degrees of freedom reside on this distant, lower-dimensional screen. This immediately reframes our understanding of what a wormhole could be. If our universe is a holographic projection, then the wormholes we picture as tunnels through three-dimensional space are merely the projected images of something else happening on that fundamental two-dimensional boundary. The startling proposal is that a wormhole is the holographic manifestation of a very specific phenomenon on that boundary, quantum entanglement. Recall the ER equals EPR conjecture we explored earlier, which linked Einstein-Rosen bridges to entangled particles. The holographic principle provides a physical and geometric framework for this connection. On the two-dimensional boundary, two widely separated points can be quantum entangled. In the holographic dictionary that translates boundary events into our three-dimensional reality, this simple, non-local connection on the flat screen is projected as a massive, geometric bridge, a wormhole connecting two distant regions in the three-dimensional bulk of the universe. The entanglement is the fundamental reality, and the wormhole is its emergent, three-dimensional shadow. To grasp this, consider a simpler holographic analogy. Imagine a two-dimensional computer screen displaying a three-dimensional video game world. In the game, your character might use a magical portal to instantly travel from a forest to a castle. On the three-dimensional game screen, this looks like a tunnel warping through the virtual landscape. But if you could look at the underlying code running on the two-dimensional hardware, you wouldn't find a tunnel. You would find a single line of code, a simple instruction that says, when the character's coordinates enter this specific pixel range, instantly change their coordinates to this other pixel range. The portal in the game is just the visual representation of that instantaneous, non-local connection in the fundamental code. Similarly, in our universe, the wormhole is the magnificent, three-dimensional visualization of a basic, entangled link on the universal boundary. This perspective elegantly resolves the spooky action at a distance of quantum entanglement. If two particles are entangled, their connection seems to violate locality because they influence each other instantly across vast distances in three-dimensional space. But from the holographic viewpoint, these two particles are not truly far apart on the fundamental boundary. Their connection is direct and local on that two-dimensional surface. The vast three-dimensional separation we perceive is the illusion, the projected image. The wormhole geometry makes this connection manifest, showing us that the two particles are, in fact, intimately connected by a geometric bridge in the higher dimensional reality that emerges from the boundary. The entanglement is the wormhole, just described in two different languages, the language of quantum mechanics on the boundary and the language of space-time geometry in the projected universe. The implications for the fabric of reality are staggering. It suggests that space-time itself is not a fundamental entity. Instead, it is an emergent property that arises from a vast network of quantum entanglement on the lower dimensional boundary. Where there is no entanglement, there is no space. This gives us a completely new way to think about the connectivity of the cosmos. The universe isn't just filled with occasional wormholes. The smooth, classical spacetime we experience every day might be maintained by a dense, underlying web of microscopic entanglement, countless tiny ER bridges that our senses perceive as continuous, empty space. A traversable wormhole, then, would not be a bizarre anomaly, but simply a region where this underlying entanglement has been amplified and organized into a macroscopic, navigable structure. The holographic principle tells us that to build a wormhole, we might not need to manipulate gravity and exotic matter directly in three dimensions. We might instead learn to engineer and control the quantum entanglement states on the two-dimensional boundary of reality, using that fundamental code to rewrite the geometric rules of the projected world we call home. Engineering our own cosmic shortcuts represents perhaps the ultimate technological dream, a feat that would transform humanity from a species confined to a single solar system into a truly interstellar civilization. Let's speculate on what it would actually take to build an artificial wormhole from scratch. The first and most daunting hurdle is the sheer scale of energy required. General relativity tells us that to significantly warp the fabric of spacetime, you need to concentrate an almost unimaginable amount of mass energy. Some theoretical estimates suggest that to create a wormhole with a throat just 1 meter wide, you might need to harness the total energy equivalent of the entire output of our sun for millions of years, or perhaps even the mass energy of Jupiter itself. This isn't just a power bill, it's a project on a stellar, even planetary scale. Science fiction often provides a visual for this, like the Dyson sphere, a hypothetical megastructure that would encapsulate a star to capture nearly all of its energy output. An advanced civilization might construct such a sphere not for mere electricity, but as a cosmic power plant dedicated to the singular task of warping spacetime. They would channel this colossal energy into a specific region, using unimaginably powerful and precise gravitational field generators to fold space and pinch it into the initial form of a tunnel. This process would be the opposite of a bomb going off. It would be an act of supreme control, a delicate sculpting of the cosmos's fundamental geometry using star-sized tools. But creating the initial warp is only half the battle. The moment the wormhole forms, the immense gravitational tension within its throat will try to snap it shut into a singularity. This is where the second and even more perplexing requirement comes in: exotic matter. As we've discussed, this isn't something you can mine from an asteroid. It's a substance with negative energy density, and you would need a staggering amount of it to line the wormhole's throat and act as a counter-gravitational force, propping the tunnel open against its own weight. One potential method for generating this exotic matter could involve manipulating quantum fields on a massive scale. We know from the Casimir effect that tiny regions of negative energy can exist. An advanced technology might learn to amplify this effect, perhaps by creating a dynamic lattice of incredibly dense energy fields that vibrate in just the right way to produce a sustained and powerful negative energy region. Think of it as using quantum resonance to tune the vacuum of space itself, coaxing it into a state that pushes outward rather than pulling inward. Another, even more speculative, approach could draw inspiration from the mysterious dark energy that permeates the cosmos. If we could ever understand the nature of this force that's accelerating the expansion of the universe, we might learn to bottle it. A dark energy reactor could, in theory, concentrate this repulsive force, channeling it into the wormhole's throat to provide the necessary stabilizing pressure. The engineering challenges here are beyond our current comprehension, involving technologies that can manipulate the fundamental properties of the vacuum on a macroscopic scale. This isn't just building a bigger rocket, it's about graduating from manipulating matter to manipulating the very stage upon which matter performs. The process of construction itself would likely be a multi-stage endeavor. The first step might involve creating a pair of microscopic wormholes using a massive particle collider of unimaginable power, perhaps one that encircles an entire planet. These nascent tunnels would be part of the quantum foam, fleeting and unstable. The next and far more difficult phase would be the inflation process. Using focused beams of exotic matter and immense energy, engineers would have to carefully expand these microscopic throats, reinforcing them as they grow to prevent immediate collapse. It would be like carefully blowing up a bubblegum bubble while simultaneously weaving a reinforcing mesh around it, all happening at a scale where the laws of quantum gravity reign supreme. Once two stable mouths are created, one of them would need to be transported to a desired location. This itself presents a monumental challenge, as moving a massive, space-time warping object would require propulsion systems that could counteract its own profound gravitational field without disrupting its delicate internal structure. The civilization that achieves this wouldn't just be building a tunnel, they would be performing the most delicate surgery on the universe itself, mastering the art of space-time engineering to weave the galaxy together. Now, let's tackle a common and crucial point of confusion that often arises when we talk about wormholes. It's the idea that zipping through one of these tunnels constitutes faster than light travel, breaking the universe's ultimate speed limit. This isn't quite right. A journey through a stable, traversable wormhole is better understood as the ultimate cosmic cheat sheet. It's not about moving faster than light, but about taking a brilliantly clever shortcut. Imagine you're in a race against a beam of light. The finish line is a star 100 light-years away. The rule is that nothing can travel through space faster than light. So the photon takes off, moving at its top speed of about 299,792,458 meters per second, and it begins the long, straight-line journey across 100 light-years of interstellar space. It'll take that photon 100 years to reach its destination. Now, imagine that the fabric of space-time between you and that star isn't flat. It's folded, like a piece of paper bent so that your starting point and the distant star are nearly touching. A wormhole is a tunnel that connects those two folded points directly. You don't travel the 100 light-year distance. You step into the tunnel here and step out there, a journey that might take you only a few minutes of your own time. To an outside observer tracking the light beam, it would appear that you arrived at the destination almost instantly, long before the light beam finished its long trek. You have effectively beaten light to the destination, not by outpacing it, but by outsmarting the course. The light beam ran the full marathon. You took a hidden subway that cut straight across town. This distinction is vital because it sidesteps one of the major paradoxes associated with true faster-than-light travel, the violation of causality, which leads to those troubling time travel paradoxes like going back and preventing your own birth. According to Einstein's special theory of relativity, if you could truly accelerate an object with mass to the speed of light, its mass would become infinite and the energy required would be infinite. More importantly, from any given reference frame, information cannot be transmitted faster than light without messing with the fundamental order of cause and effect. However, when you use a wormhole, you are not locally exceeding the speed of light within your own region of space. From your perspective inside the spacecraft, you might be moving at a perfectly mundane, safe speed. The magic isn't in your engines, it's in the geometry of the path you're taking. The wormhole itself does the heavy lifting of warping space-time, providing a contracted path that dramatically reduces the proper distance you need to travel. You are simply moving through a region of space that has been topologically rearranged to bring two distant points into close proximity. Think of it using a classic analogy. Picture a worm burrowing through an apple. The ant on the surface has to walk the entire curved circumference to get from one side to the other, but the worm can chew a hole straight through the core, arriving in a fraction of the time. The ant didn't get slower and the worm didn't get faster. The worm just took a more direct route through a dimension the ant on the surface couldn't access. In this analogy, the three-dimensional space of the apple is like our four-dimensional space-time. The wormhole provides a shortcut through a higher dimensional bulk, allowing for a journey that seems impossibly quick from the perspective of someone confined to the surface of the universe. Your travel time through the wormhole is your proper time, and it can be very short, but at no point does your speedometer ever read a value greater than the speed of light. The phenomenal feat is the wormhole's existence, not your velocity while passing through it. So, what would this experience actually be like for a traveler? You approach the mouth of the wormhole, which from the outside might look like a shimmering sphere, a gravitational lens distorting the starlight behind it. You cross the threshold, not into a tunnel of swirling colors as often depicted in movies, but into a region of space where the geometry is profoundly warped. The journey through the throat might feel instantaneous, or it might take a subjective amount of time depending on the specific physics of the wormhole. Throughout this transit, your ship's instruments would never register a velocity exceeding light speed. The true wonder would be the view out your window. Looking back toward the entrance, you might see a rapidly shrinking circle of light from your home universe. Looking forward, you might see the exit mouth growing larger, revealing the destination star system. Because the wormhole connects 2 points in spacetime, the light from the destination is reaching you through the short tunnel, not the long external route, allowing you to see your target almost immediately. You emerge having covered a vast cosmic distance in a time that seems impossibly brief, all while strictly obeying the universal speed limit. You haven't broken the laws of physics. You've simply used a profound understanding of those laws to find a loophole, turning a million-year journey into a day trip. Building on the idea of black holes as potential gateways, we arrive at a truly profound hypothesis that blurs the line between destruction and passage. This is the theory of black hole-wormhole duality, a concept suggesting that these two cosmic phenomena might not be distinct entities at all, but rather different faces of the same fundamental object. At first glance, a black hole and a traversable wormhole seem like opposites. One is a gravitational prison from which nothing escapes, a cosmic endpoint. The other is a doorway, a promise of connection and transit. Yet, when we push our theories to their limits, this clear distinction begins to dissolve, leading to a revelation that could solve one of the most stubborn puzzles in modern physics: the black hole information paradox. The paradox itself strikes at the heart of the conflict between general relativity and quantum mechanics. According to Einstein's theory, when a star collapses into a black hole, all the information about that star, every detail about the atoms that formed it, their arrangement, their history, is lost forever behind the event horizon. The black hole can be described by just three simple properties: its mass, its electric charge, and its spin. From the outside, it's the most featureless object in the universe. But quantum mechanics has a foundational rule: information cannot be destroyed. The quantum state of a system must evolve in a smooth, predictable way. You should always, in principle, be able to run the clock backward and figure out what the initial state was. So, what happens to all the intricate information about the book you just threw into a black hole? Does it truly vanish, erased from reality? For decades, this conflict suggested that one of our two most successful theories of physics was fundamentally flawed. The black hole-wormhole duality offers a breathtakingly elegant escape from this conundrum. It proposes that the information swallowed by a black hole is not lost. Instead, it is meticulously preserved and transferred. Imagine a black hole in our universe not as a bottomless pit, but as one mouth of a wormhole. The other mouth could exist in a completely different region of our cosmos, or even in a separate universe altogether. In this picture, when matter and energy cross the event horizon, they don't travel to a singularity to be crushed into non-existence. Instead, they journey through the wormhole's throat and are ejected from the other side. The black hole isn't a final destination. It's a grand central station in a vast cosmic transit network. The information about every particle that falls in is not destroyed but simply relocated, emerging from the linked wormhole exit, thus perfectly obeying the quantum law that information must be conserved. This idea finds a powerful voice in the work of physicists like Juan Maldacena and Leonard Susskind, who have explored this duality through the lens of string theory and the holographic principle. Their research suggests that the interior of a black hole, the region behind the event horizon, might be physically equivalent to a different universe or a remote part of our own, connected via a wormhole. This isn't just a clever metaphor, it's a proposed mathematical equivalence. The physics describing the chaotic interior of a complex black hole could be perfectly mapped onto the physics of a different, seemingly separate system. The event horizon, in this view, acts as a kind of translator, encoding the information of infalling objects and transmitting it through the wormhole bridge to be reconstructed on the other side. The black hole and the wormhole become two different descriptions of the same underlying reality. Think of it like a mysterious one-way office building. From the outside, you see a single, imposing front door, the event horizon. People go in, but they never come back out. It appears to be a place of utter consumption. But what if this building has no internal rooms? What if the moment someone steps through the front door, they are instantly teleported to a completely different city, appearing out of a corresponding doorway there? To an observer standing outside the original building, It looks exactly like a black hole, a place of no return. But from a global perspective, it's a transportation system. Nothing is being destroyed, everything is just being moved. The black hole-wormhole duality suggests our universe might be wired in exactly this way, with every apparent point of destruction secretly being a point of transfer. This has a stunning implication for the end of a black hole's life. As Stephen Hawking taught us, black holes aren't completely black, they slowly evaporate by emitting Hawking radiation. This is a quantum effect where particle-antiparticle pairs pop out of the vacuum near the event horizon, with one particle falling in and the other escaping. Over trillions of years, this process causes the black hole to lose mass and eventually vanish. The original information paradox asked what happened to all the information about the stuff that fell in. If the black hole just disappears, the information seems to be truly lost. But if the black hole is secretly a wormhole, the resolution is clear. The information isn't stored in the Hawking radiation in some scrambled, obscure code. Instead, as the black hole evaporates, the wormhole connection becomes the primary reality. The information is not in the radiation itself. It has already been safely transferred through the wormhole to its linked exit during the infall process. The evaporation is just the closing of the front door after the last guest has already been teleported away. The information was never in danger of being lost because it was never truly inside the black hole in the first place. It was always in transit. This perspective transforms our understanding of causality and the fabric of the cosmos. It suggests that what we perceive as the most destructive regions of the universe are in fact the most profound connectors. A black hole's event horizon is not a wall but a gateway, and its terrifying gravity is not a crusher but an accelerator on a cosmic highway. The duality paints a picture of a deeply entangled universe where the fate of information is always secure, woven into the very geometry of space-time through these hidden bridges. While the journey through a realistic black hole would still be lethal due to intense tidal forces and radiation, the theory assures us that on a fundamental level, the cosmos is preserving its story. The universe, it seems, keeps perfect records not in ledgers of light but in the timeless architecture of wormholes, ensuring that no chapter of its history is ever truly erased. To truly grasp how string theory reimagines the wormhole, we must first step beyond the familiar three dimensions of our daily experience. This framework proposes that the fundamental ingredients of the universe aren't point-like particles, but unimaginably tiny, vibrating loops of energy strings. And for the mathematics of these strings to be consistent, they must vibrate not in 3 spatial dimensions, but in 10 or even 11. Our reality, with its up-down, left-right, and forward-backward, is just a 3-dimensional slice of a far richer, higher-dimensional cosmos. The reason we don't perceive these extra dimensions is that they are compactified, curled up into a space so incredibly small, on the order of the Planck length, that they are completely hidden from our view. In this paradigm, a wormhole is no longer just a tunnel through the warped space-time of our 4-dimensional world. It becomes a structure that can navigate this grander, higher-dimensional geography. The fabric of the cosmos isn't a simple sheet. It's a complex, multidimensional landscape, and wormholes could be the pathways that connect its most distant valleys. This leads us to one of the most powerful concepts in modern string theory, the brain. Short for membrane, a brain is a dynamic object that can have multiple dimensions. Our entire universe, with all its stars, planets, and galaxies, could be a 3-dimensional brain, often called a 3-brain, floating within a higher dimensional expanse known as the bulk. Imagine our universe as a single, impossibly vast slice of bread adrift in a higher dimensional loaf. Now, picture another slice of bread floating parallel to ours. That could be another universe, another 3-brain with its own stars and physical laws, completely separate from our own. In our everyday experience, we are confined to our own brain, like ants crawling on the surface of a leaf. utterly unaware of the other leaves on the tree. The forces we know, like electromagnetism and the nuclear forces, are like glue that binds us to this surface. Their particles are open strings whose endpoints are stuck to our brain. Only gravity, described by closed strings, can leak out into the bulk, which is why it feels so weak compared to the other fundamental forces. This is where the wormhole concept undergoes a spectacular transformation. In the brain world scenario, a wormhole could be a tunnel that forms not just within our brain, but between two different brains. It would be a bridge made of space-time that arcs through the higher dimensional bulk, connecting our universe directly to another. Think back to the analogy of the apple and the worm. The ants on the skin of the apple are like beings confined to their brain. A wormhole within the skin allows them to shortcut across their own surface. But a wormhole that tunnels through the bulk is like the worm burrowing through the juicy interior of the apple to connect to a completely different apple altogether. This isn't just a shortcut across space, it's a gateway to another reality. The creation of such a structure could be a violent, high-energy event in the early cosmos, perhaps a cosmic collision between brains or a quantum gravitational fluctuation so profound that it punched a stable hole between them. Now, how would strings and brains themselves be involved in creating or traversing such a tunnel? The vibrational patterns of fundamental strings are everything in this theory. Different vibrations correspond to different particles. A graviton, the hypothetical particle that carries the gravitational force, is a specific vibrational state of a closed string. As these closed strings move through the bulk, they could, in principle, carry gravitational influence between brains. To form a stable, traversable wormhole, however, you would likely need the brain itself to warp in a specific way. Imagine our three-brain not as a perfectly flat sheet, but as a flexible membrane. Under certain conditions, perhaps influenced by immense concentrations of energy or the presence of other brains, our brain could develop a throat that extends out into the bulk, reaching toward another brain. This throat would be the wormhole. The exotic matter needed to keep it open could arise from the specific properties of the strings and brains themselves, perhaps from the tension of the brain or from the complex interplay of string vibrations within the throat, naturally providing the negative energy density required for stability. The potential for travel through such a structure is as mind-bending as its formation. A spacecraft wouldn't simply fly through empty space within the tunnel. The journey would involve moving through a region where the very definition of location shifts from the coordinates of our brain to those of the higher dimensional bulk. As the ship entered the wormhole's throat, it would effectively be transitioning from being firmly anchored to our brain to moving freely through the bulk, guided by the warped geometry of the connecting bridge. This wouldn't be a simple ride. It might require technologies that can manipulate the brain's structure or shield the vessel from the intense string scale effects at the throat's narrowest point. Successfully navigating this passage would mean arriving at the other mouth, which would be an opening onto a different brain, a parallel universe that could have physical constants, particles, and even a number of macroscopic dimensions entirely different from our own. The wormhole, in the context of string theory, becomes the ultimate passport, not just to other stars, but to other creations, revealing a cosmos of literally unimaginable diversity. This idea that entanglement and wormholes might be two sides of the same coin brings us to one of the most elegant analogies in all of theoretical physics, drawing a stunning parallel between the science of teleportation and the architecture of spacetime itself. We've explored the profound ER equals EPR conjecture, but now let's see how it plays out in a real world, or rather, a real quantum world scenario. This is the theory of quantum teleportation, a verified protocol that doesn't move matter, but instantly transfers the complete quantum state of a particle from one location to another. At its heart, this process relies entirely on the spooky link of entanglement, and through the lens of modern physics, this might be because a microscopic wormhole is silently doing the work behind the scenes. To understand this, let's walk through how quantum teleportation actually works, stripping away the complex math to reveal its core principles. Imagine you have a particle, let's call it particle A, whose quantum state you want to teleport. This state is a fragile combination of properties like spin and polarization, a unique quantum identity you wish to preserve. You can't just scan it and send a blueprint because the very act of measuring a quantum state collapses it, destroying the original information. This is where a pair of entangled particles comes in. We'll call them particle B and particle C. These two are created together, their fates forever linked. You take particle B and keep it with you right next to particle A. Your colleague takes particle C and travels to the other side of the galaxy. Now you perform a special kind of joint measurement on particle A and your particle B. This measurement does two crucial things. It entangles particles A and B, and in doing so, it destroys the original state of particle A. But here's the magic. The moment you make that measurement, particle C, all the way across the galaxy, instantly changes. It is transformed into an exact replica of particle A's original quantum state. The information hasn't traveled through the space between you and your colleague. It has, in effect, bypassed it entirely, appearing instantaneously at the distant location. Now, let's reimagine this entire process through the geometric lens of the ER equals EPR conjecture. According to this radical idea, your entangled particles B and C aren't just spiritually linked by an invisible thread. They are physically connected by a microscopic Einstein-Rosen bridge, a Planck-scale wormhole. In this geometric picture, the entire teleportation protocol looks completely different. When you want to teleport the state of particle A, you don't send a signal. Instead, you perform the measurement that essentially feeds particle A into the wormhole mouth represented by particle B. Because particles B and C are two ends of the same geometric structure, the information about particle A's state naturally and instantly emerges from the other mouth, particle C. The wormhole acts as a pre-existing shortcut, a private channel through the geometry of spacetime that allows the quantum information to bypass the vast external distance. The spooky action at a distance is demystified. It's not spooky at all, but a direct consequence of a hidden geometric connection. This analogy transforms our understanding of what's happening during teleportation. We usually visualize the three particles as separate points in space with lines of influence connecting them. The geometric view suggests this picture is a flawed illusion, a projection of a deeper reality. A more accurate, though stranger, visualization is that particles B and C are not truly independent entities. They are like the two visible tips of a single, subsurface structure, the two ends of a submicroscopic tunnel in the quantum fabric of space. The teleportation of particle A's state isn't a jump across space, but a passage through this ultra-short bridge. From the perspective of the information being teleported, it only had to travel a tiny Planck-length distance through the wormhole throat, not the million-light-year journey through regular space. This explains the instantaneous correlation without violating the speed of light. The information took a breathtakingly short cut. The implications of this are staggering, not just for teleportation, but for the nature of reality itself. It suggests that the quantum connections we use in our most advanced laboratories are not abstract correlations, but are underwritten by the fundamental geometry of the universe. Every time we successfully perform quantum teleportation, we might be providing indirect experimental evidence for the existence of these Planck-scale wormholes. We are effectively using a microscopic spacetime tunnel to transfer information, even if we can't see or traverse it ourselves. This paints a picture of a cosmos that is fundamentally woven together not by empty void, but by an unimaginably dense and dynamic network of these tiny bridges, a quantum entanglement that is quite literally the thread from which the tapestry of space is sewn. But if wormholes are a plausible feature of our universe capable of connecting its farthest reaches, then their existence might hold the key to answering one of the most haunting questions in all of science: where is everybody? This is the Fermi paradox, the perplexing contradiction between the high probability of intelligent alien life emerging in our vast, ancient galaxy and the utter lack of any observable evidence for it. If the cosmos is teeming with life, why does it seem so silent and empty? A compelling speculative answer lies in the very technology we've been exploring. Perhaps advanced civilizations aren't using starships to slowly plod across the interstellar void. Maybe they graduated from that eons ago, having instead built a permanent, stable network of wormholes. This wouldn't just be a more efficient way to travel, it would fundamentally change the nature of their presence in the galaxy, rendering their activities almost invisible to our current methods of detection. Consider our own civilization's approach to space exploration. We build telescopes to look for distant planets and listen for radio signals. We dream of constructing giant generation ships that would take centuries to reach another star. This is a paradigm rooted in crossing external space, a method that leaves traces. A powerful laser beacon, the thermal signature of a massive spacecraft, or the radio chatter of a growing colony would all be potential signs of life. But a civilization that has mastered wormhole technology operates on an entirely different level. They wouldn't be sailing across the ocean, they'd be using a subway system. There would be no need for them to broadcast powerful signals across light years to communicate with their colonies, because their wormhole network would provide instantaneous point-to-point links. Communication would be as local and undetectable as a fiber optic cable is compared to a sky-filling radio tower. Their interstellar trade, cultural exchange, and even governance would happen through these private tunnels, leaving no electromagnetic signature for our radio telescopes to accidentally intercept. This wormhole transit system would also make the concept of a starship largely obsolete, at least in the form we imagine. Why would an advanced species invest colossal resources in building vessels that take thousands of years to reach their destination when they can simply step through a gateway and arrive instantly? The kind of propulsion systems that would be visible to us, like the hypothetical interstellar ramjets that scoop up hydrogen from space or antimatter engines releasing intense gamma-ray bursts, would simply not be in use. The most dramatic and energetic phase of their expansion, the one that might have been most detectable, would have been in their distant past when they first built the network. Once the infrastructure is in place, the galaxy becomes a settled, interconnected neighborhood, not a frontier to be constantly crossed with visible, long-duration voyages. Our current search for technosignatures is like listening for the sound of horse-drawn carriages on a highway. The traffic is still there, but it's moved to a different, silent layer of technology we cannot perceive. Furthermore, the very placement of these wormhole mouths could explain our apparent isolation. An advanced civilization would likely position the entrances and exits to their transit network in gravitationally stable, but otherwise quiet locations. The Oort cloud at the edge of a solar system, for instance, or orbiting a cold, brown dwarf star would be ideal. These are places far from the bright, noisy inner systems where young, emerging species like us might be looking. They would be the equivalent of building a major airport away from a city center to avoid congestion and prying eyes. Our telescopes are overwhelmingly focused on habitable zones around stars, searching for biosignatures in atmospheres or the structured light of cities on the night side of planets. We are not systematically scanning the dark, cold voids between stars for the subtle gravitational lensing effects that might betray a stable wormhole mouth. Our search parameters are fundamentally mismatched to the infrastructure of a galaxy-spanning wormhole network. This theory also offers a potential resolution to the great filter component of the Fermi paradox, which suggests that some almost insurmountable barrier prevents civilizations from reaching an interstellar stage. Perhaps the filter isn't death but transcendence. The development of a stable wormhole network might represent such a profound technological and societal leap that a civilization effectively graduates from the visible, expansive phase we associate with interstellar ambition. Once connected, their goals and energies might turn inward toward pursuits and dimensions of reality we cannot yet conceive. They wouldn't be driven to physically colonize every available planet because their wormhole links give them access to the resources of countless worlds without the need for local settlement. Their empire would be a networked one, a series of interconnected nodes rather than a visibly sprawling stain across the galactic disk. From our external viewpoint, it would seem as if they simply vanished when in reality, they had just stepped into the cosmic subway, leaving the surface streets empty and quiet. The silence of the cosmos, then, may not be a sign of our loneliness, but rather the hallmark of a galaxy that has already been fully connected, its vibrant interstellar community humming along just beneath the threshold of our perception. Returning from the cosmic scale of galactic networks, we find our attention pulled in the opposite direction, toward a phenomenon so subtle it unfolds in the emptiness between two tiny metal plates. This is the Casimir effect, and while it's a well-established quantum curiosity in the lab, its implications for creating and stabilizing microscopic wormholes are nothing short of revolutionary. To see the connection, let's revisit what this effect actually shows us. In a perfect vacuum where we classically expect nothing to exist, quantum field theory tells us that the void is actually alive with activity. Virtual particle pairs constantly flicker into and out of existence, borrowing energy from the vacuum for a fleeting moment. Now, place two perfectly smooth, uncharged plates extremely close together, closer than the width of a human hair. This confinement restricts the kinds of quantum fluctuations that can occur in the narrow gap between them. Only virtual particles with very short wavelengths can appear there, while outside the plates, particles of all wavelengths can fluctuate freely. This imbalance creates a tiny but measurable force that pushes the plates together. The truly crucial part for wormhole physics is the energy picture. The region between the plates has a lower energy density than the surrounding vacuum. It's a small, laboratory-produced pocket of negative energy density, the very exotic ingredient we need to prop open a wormhole's throat. Now, let's push this idea into the realm of the theoretical. If the Casimir effect can generate a minute amount of negative energy in a flat space, could we somehow use this principle to warp space itself into a tunnel? The concept involves manipulating this effect on a microscopic scale to create a rudimentary, fleeting wormhole. Imagine not two flat plates, but a pair of microscopic, spherical conductors or some other intricate nanostructure designed to concentrate the Casimir force. The intense, localized negative energy density in the infinitesimal gap between these structures could, in theory, be enough to create a tiny pinprick in the fabric of space-time, a microscopic wormhole connecting 2 points a minuscule distance apart. This wouldn't be a tunnel you could see or travel through. Its throat would be on the order of the Planck length, but its existence, however fleeting, would be a monumental proof of concept. It would demonstrate that the fundamental physics required to create a wormhole is not forbidden. It's just incredibly difficult to engineer. Scaling this effect up from a microscopic fluctuation to a usable passageway is where the theoretical challenge becomes almost unimaginably vast. The negative energy generated in a standard Casimir experiment is extraordinarily weak. To stabilize a wormhole with a throat just 1 meter wide, you wouldn't just need a slightly stronger version of this effect. You would need to concentrate negative energy on a scale that dwarfs the mass of Jupiter. One speculative idea involves not using solid plates, but rather dynamic electromagnetic fields. By arranging complex, oscillating fields in a precise configuration, it might be possible to create a region of sustained and amplified negative energy density, essentially creating a Casimir cavity without physical walls. The energy requirements for such a setup would be astronomical, potentially requiring the entire output of a star to power the field generators. This transforms the problem from one of pure theory into one of cosmic engineering, suggesting that a future civilization wouldn't just discover wormholes but would have to build them, using the Casimir effect as a fundamental blueprint for twisting the quantum vacuum into a gateway. The true power of this theory, however, may not lie in building giant wormholes, but in finally giving us a way to test these fantastical ideas in a laboratory setting. For decades, wormholes have been purely mathematical constructs. The Casimir effect provides a potential bridge between abstract equations and experimental physics. Researchers are already investigating how the presence of such extreme negative energy densities could leave a detectable signature. One proposal involves looking for specific disturbances in quantum fields that would only occur if a micro-wormhole briefly formed and evaporated within the Casimir cavity. Another approach considers the gravitational implications. Even a microscopic wormhole would warp space-time in its immediate vicinity. While the effect would be incredibly small, ultra-sensitive instruments designed to measure minute gravitational anomalies or shifts in the Casimir force itself might one day pick up the signature of a space-time tunnel being born and dying in a fraction of a second. Finding such evidence would do more than just confirm a prediction. It would fundamentally change our understanding of the vacuum, proving that empty space is not just a stage, but a dynamic, structured medium capable of supporting the most incredible topological phenomena. This interplay between the Casimir effect and wormholes also provides a fascinating link to the concept of quantum foam. You'll recall that at the Planck scale, spacetime is thought to be a turbulent sea of virtual black holes and wormholes, constantly bubbling up and disappearing. The negative energy we see in the Casimir effect is a direct manifestation of the same quantum fluctuations that make up this foam. In a sense, when we conduct a Casimir experiment, we are not creating something from nothing. We are simply taming and amplifying a process that is happening everywhere all the time at the very smallest scales of reality. The tiny region of negative energy between the plates is a controlled glimpse into the seething quantum foam. By learning to manipulate this effect, we are not inventing a new physics. We are learning to sculpt a material that has always been there, hidden in the fabric of the void. This perspective suggests that the path to macroscopic wormholes may not be one of brute force construction, but of delicate amplification, learning to nurture a naturally occurring quantum wormhole, using effects like Casimir negative energy to gently encourage it to grow and stabilize, rather than collapse back into the frothing vacuum from which it came. Now, while these tiny quantum wormholes may be beyond our direct sight, there is a way we might spot a much larger one hiding in the depths of space. This brings us to a fascinating method of detection that relies on one of astronomy's most powerful tools, not to look for the wormhole itself, but to observe how its immense gravity bends the very light traveling around it. The key is a phenomenon called gravitational lensing, a dramatic confirmation of Einstein's theory that massive objects warp the fabric of spacetime. We already see this effect with galaxies and galaxy clusters, which act like cosmic magnifying glasses, distorting and amplifying the light from objects behind them into beautiful arcs and rings. A wormhole possessing the gravity of a massive object would create its own unique lensing signature, and it's in the peculiar details of that distortion that we might find our first proof. Imagine a distant, brilliant quasar, a beacon of light from the early universe. Normally, we see it as a single, steady point. Now, imagine a wormhole drifting silently through the interstellar medium, its path carrying it directly between us and that far-off quasar. As it moves into alignment, its gravitational field begins to act like a strange and complex lens. Unlike a single massive object like a black hole, which typically creates a single, smeared Einstein ring around it, a wormhole's geometry is fundamentally different. It has two distinct mouths connected by a throat. This unique structure means that light from the background quasar can take not one, but two very different paths to reach our telescopes. Some light rays will simply bend around the gravitational well of the mouth closest to us, creating one distorted image. But other light rays can do something truly extraordinary. They can actually pass through the wormhole itself. This creates a second, completely separate light path. A photon from the quasar could enter the distant mouth, travel through the tunnel, and exit from the mouth nearer to us, continuing on its journey to Earth. From our perspective, this would appear as a second, ghostly image of the same quasar, appearing right next to the first one. We wouldn't see a tunnel. We would see a double image or a complex multiple image system that defies explanation by a single spherical lens. The image that passed through the wormhole might also have unique properties. Because it traveled through the ultra-warped spacetime inside the throat, its light could be stretched or compressed in unusual ways, exhibiting a spectral signature or a time delay that's different from the light that simply went around. Astronomers are actively developing the techniques to search for these subtle anomalies. They're using powerful telescopes to monitor millions of stars and galaxies, looking for the telltale, temporary brightening and splitting that would occur as a massive, compact object like a wormhole passes in front of them. The challenge is immense, as we'd need to distinguish a wormhole signature from other exotic objects like solitary black holes or dense clumps of dark matter. But the hunt itself pushes the boundaries of our observational capabilities, turning the entire sky into a laboratory for testing the most extreme predictions of general relativity. Finding that one perfect, inexplicable double image in the vast cosmic archive would be more than just a discovery. It would be a revelation, proving that the universe's most fantastical shortcuts are not just equations on a page, but real, tangible structures waiting in the dark. But if the Novikov principle maintains a consistent timeline, it introduces a different kind of puzzle, one that challenges our very notion of origin and invention. This is the bootstrap paradox, a mind-twisting loop of causality that becomes terrifyingly possible with a wormhole time machine. Imagine a brilliant young physicist, let's call her Anya, toiling away in her laboratory. She is desperately trying to solve the equations for stabilizing a wormhole's throat, but the solution eludes her. One evening, an older, weathered version of herself appears from a shimmering portal in her lab. This future Anya doesn't say a word. She simply hands her younger self a data chip containing the complete, flawless blueprint for a traversable wormhole machine. Then she steps back through the portal and vanishes. The young Anya, now armed with the answer, spends the next several decades building the machine exactly as specified. The day it is completed, she activates it, steps through, and arrives at that precise moment in her own past to deliver the very same data chip. The critical, brain-breaking question is this: who actually invented the wormhole blueprint? The information on that chip had no beginning. It was never created by anyone. It simply exists trapped in an endless closed loop, forever being handed from an older self to a younger self. The artifact, or the information, is said to be bootstrapped into existence, like pulling yourself up by your own bootstraps, a logical impossibility that time travel makes physically possible. This paradox isn't just about blueprints. It can apply to anything from a physical object to a simple melody. Think of a famous composer in the 17th century who is struggling with writer's block. A time traveler from our era, a fan of classical music, visits him and hums the complete melody of Beethoven's Fifth Symphony. The composer, astonished by its brilliance, writes it down and publishes it as his own work. The symphony becomes a timeless classic, passed down through the centuries until our time traveler, in their own youth, hears it and learns to love it. They then carry it back in time to give to the composer. So, who truly composed this iconic piece of music? The loop is perfectly consistent. The music exists, but it has no point of origin. It is a cosmic orphan, a piece of cultural information that authored itself. In the context of wormholes, this could mean that pivotal technologies, profound works of art, or even entire fields of scientific knowledge might not be inventions at all, but rather discoveries of information that has always been circulating in time, waiting to be found and then returned to its starting point. The philosophical implications of this are staggering, forcing us to confront what we mean by creation and identity. Our entire understanding of human progress is built on a linear model of cause and effect. A genius has an idea which builds upon previous ideas, pushing knowledge forward. The bootstrap paradox shatters this model. It suggests that progress could, in some cases, be an illusion, a mere recitation of a pre-recorded script. If you receive the secret of faster-than-light travel from your future self, can you truly claim to be a pioneer? Your achievement feels real, your effort was genuine, but the spark of genius, the foundational breakthrough, was never yours. It calls into question the nature of free will within such a loop. Did Anya have any choice but to build the machine and deliver the chip? The timeline's consistency seems to demand it, turning what feels like a series of choices into a single, immutable event playing out across time. Your life's work becomes a fixed part of a temporal mosaic, where you are both the artist and a brushstroke applied by your own future hand. Furthermore, the paradox challenges the very concept of knowledge itself. We typically believe that information is created through a process of deduction, experimentation, and insight. But in a bootstrapped loop, information exists without ever having been generated. This leads to a profound question: does all information need an origin? The bootstrap paradox suggests that some information can be acausal, disconnected from the chain of cause and effect that we rely on to make sense of the world. It simply is. For a universe that permits wormhole-based time travel, such ontological paradoxes might not be errors or flaws, but rather fundamental features of a more complex, non-linear reality. The universe, in this view, could be filled with these self-justifying loops where the question, "Where did this come from?" has no meaningful answer. The existence of the loop is the only truth, a perfect and maddening circle that defies our deepest intuitions about how reality should work. This brings us to a profound puzzle that connects the architecture of wormholes to one of the most fundamental rhythms of our universe, the relentless one-way march of time. We're talking about the thermodynamic arrow of time, the principle that entropy, a measure of disorder, always increases in an isolated system. It's why an ice cube melts in a warm room but never spontaneously refreezes, why we remember the past but not the future, and why the universe as a whole is evolving from a state of low entropy at the Big Bang toward a state of maximum entropy, a final heat death. This arrow gives our lives and the cosmos a clear direction, a narrative flow from order to disorder. So, what happens to this deeply personal and cosmic experience of time's flow when you step into a wormhole, a structure that can, in theory, connect different moments in the timeline? The question isn't just whether you travel to the past or future, but how your own internal arrow of time, your personal journey from cause to effect, interacts with the wormhole's warping of causality. Let's consider the first possibility, that traversing a wormhole preserves your personal arrow of time. Imagine you enter a wormhole mouth here on Earth in the year 2040. You travel through the tunnel and emerge from the other mouth in the Andromeda Galaxy in the year 2020. From the perspective of the external universe, you have traveled 10 years into the past. But from your own internal perspective, what do you experience? In this scenario, your subjective timeline remains perfectly intact and continuous. The moments flow for you in the same order they always have. You feel the seconds tick by inside the wormhole just as you would on a spaceship. You step out into Andromeda, and your memory is of having just left Earth in 2040. Your personal entropy, the complex order of your body and mind, continues on its natural path of increasing. You still age, your brain cells fire in the same sequence, and you remember the future of Earth as your own past. In this view, the wormhole is simply a bridge that connects two different points in the external, universal timeline. Your local experience of cause and effect is never violated. You could, in theory, meet your younger self in Andromeda, and while it would be a bizarre encounter, your own internal chronology would remain perfectly logical and consistent. You would carry the memories of a future that, for your younger self, has not yet happened, but for you is an unchangeable part of your personal history. Now, let's explore the far more disorienting alternative that a wormhole journey could actually reverse your personal arrow of time. This is a concept that pushes the limits of what is physically conceivable. In this scenario, as you cross the threshold of the wormhole, the very direction of thermodynamic processes for you and your ship would flip. From your perspective, time would appear to run backward. The entropy of your local system would begin to decrease. Imagine the bewildering sensory experience. Scattered light rays would converge into your ship's headlights. Exhaled carbon dioxide would flow back into your lungs, and your thoughts would seem to unfold in reverse order, with you remembering the future and anticipating the past. This reversal wouldn't just be an illusion, it would be a fundamental rewiring of causality within your immediate reference frame. The cup of coffee you spilled just before entering the wormhole would, from your point of view, spontaneously reassemble from the puddle on the floor and leap back into your cup. This possibility arises from the complex geometry of certain wormhole solutions in general relativity, where the path through the tunnel could force a traveler's world line to become time-like in a reversed orientation relative to the external universe. The implications of such a reversal are philosophically staggering. If you were to emerge from the wormhole after such an experience, which version of you would step out? Would it be the you who remembers leaving Earth, or a you whose consciousness has been completely inverted, remembering a future that everyone else sees as the past? The very concept of personal identity, which is so tightly bound to our linear experience of memory and anticipation, would be shattered. This scenario also creates a profound conflict with the global arrow of time of the universe. The second law of thermodynamics is a statistical law. It's not impossible for entropy to decrease locally, just incredibly, astronomically improbable. For your entire spacecraft and body to experience a coordinated reversal of entropy would require an unimaginable conspiracy of quantum events, effectively forcing all the particles in your body to retrace their paths in perfect synchrony. Most physicists consider this possibility to be effectively forbidden, not by the equations of general relativity per se, but by the overwhelming statistical weight of the second law. The universe's headlong rush toward greater disorder is a powerful current, and swimming upstream to this degree is seen as virtually impossible. This tension between local and global time arrows leads us to what is likely the most widely accepted theoretical resolution. The universe's overall arrow of time, set by the incredibly low entropy initial conditions of the Big Bang, acts as a dominant background that all local processes must ultimately respect. Even if a wormhole allows for travel to an external past, your journey through it would still be a process that contributes to the total entropy of the entire connected system. The energy required to stabilize the wormhole, the radiation it might emit, and the very act of your passage would all generate heat and disorder. So, while you might arrive at a coordinate in the past from an external clock's perspective, your personal timeline and the thermodynamic processes within your body would remain steadfastly aligned with the universe's overarching march toward higher entropy. You would carry a little bubble of increasing disorder from the future into the past. Your arrival in 2020 would not violate the second law because your presence itself represents a local increase in entropy for that era. You are a complex, ordered system from the future that has been injected into the past, and your subsequent actions will only create more disorder from that point forward. The universe's total entropy continues to increase, even if its history, from a God's eye view, contains loops and walls made possible by wormholes. This perspective provides a fascinating way to reconcile time travel with the second law. The past you visit is not a pristine, low-entropy state that you are contaminating. In the context of a universe with wormholes, that past moment was always destined to receive you. Your journey is part of the single, consistent timeline, and the entropy of that past moment with you in it is exactly what it needs to be consistent with the higher entropy future from which you came. The wormhole, therefore, doesn't allow you to escape the arrow of time. It simply allows for a more complex, looped geometry along which that arrow consistently points. Your personal experience of cause and effect remains unbroken, and the universe's story of increasing disorder continues unabated, just along a more intricately woven narrative path than we once could have imagined. But our exploration of black holes and their hidden connections brings us to a fundamental principle that seems to define their ultimate simplicity, a rule that might also hold the key to understanding what truly distinguishes a wormhole. This is the famous no-hair theorem, a profound result in general relativity that tells us that black holes are, in a sense, the most featureless objects in the universe. Once matter or energy falls past the event horizon, all the intricate details about it, what kind of star it was, its chemical composition, whether it was shaped like a sphere or a pretzel, are completely lost. The black hole doesn't care. It forgets everything except for three, and only three, defining characteristics: its total mass, its electric charge, and its angular momentum or spin. That's it. All the hair, a physicist's playful term for any other distinguishing details or information, is shaved away. A black hole has no memory, no personality, no unique identity beyond these three numbers. It is the ultimate cosmic tabula rasa, a perfect blank slate defined by sheer gravity. Now, let's apply this radical concept of simplicity to the far more complex and speculative object we've been discussing. If a wormhole is, in some models, deeply related to a black hole, perhaps even sharing an event horizon, does the no-hair theorem apply to it as well? Would a wormhole also be a bald, featureless portal, or could it possess a rich head of hair? This question isn't just academic. It cuts to the very heart of what a wormhole is and what it could do. If wormholes are forced to obey the no-hair theorem, then every wormhole with the same mass, charge, and spin would be utterly identical. There would be no way to tell one from another, no way to know where its other end might lead just by looking at its entrance. It would be like having a network of identical, unmarked doorways, with no signs indicating whether they open onto a peaceful garden or a raging inferno. This would make them incredibly dangerous and unpredictable tools for travel. However, the very nature of a traversable wormhole suggests that it must violate the spirit, if not the letter, of the no-hair theorem. Remember, for a wormhole to be stable and navigable, its throat must be lined with exotic matter. This exotic matter isn't just a passive component. Its specific configuration, its quantum state, and its distribution could very well act as a form of hair. This exotic matter, hair, could encode information about the wormhole's structure, the length of its tunnel, the location of its other mouth, and even the properties of the space-time region it connects to. Think of it like the wiring and insulation inside an electrical cable. From the outside, two cables might look identical, but their internal structure determines what kind of data they can carry and where they plug in. Similarly, the exotic matter lining could be what gives a wormhole its unique address on the cosmic network, a set of additional parameters that carry the information the no-hair theorem supposedly erases. This idea connects back to the black hole information paradox and the holographic principle. The modern resolution to the paradox suggests that information isn't actually lost in a black hole, it's somehow encoded on the event horizon. In the language of the ER equals EPR conjecture, this information is preserved in the quantum entanglement that forms the microscopic wormholes connecting the horizon to the Hawking radiation. So, in a sense, a black hole does have hair, but it's not the kind of classical hair the original theorem described. It's quantum hair, subtle correlations and entanglement patterns that distinguish one black hole from another, even if their mass, charge, and spin are identical. If a traversable wormhole is a stabilized version of such a structure, then its hair would be this full, rich quantum information, potentially accessible and readable. A stable wormhole wouldn't just be a tunnel, it would be a library, its walls inscribed with the data of everything that ever fell into it or passed through it, a permanent record of its history and connections written in the language of quantum geometry. Now, let's shift our perspective from the wormhole as a cosmic subway to the wormhole as perhaps the ultimate supercomputer, a natural processor woven from the fabric of space-time itself. This speculative theory pushes beyond transportation to propose that the complex, folded geometry inside a wormhole might not just be a passageway, but a dynamic system capable of performing unimaginably complex calculations. Think of it not as a tunnel with static walls, but as a labyrinthine circuit board where the very warping and vibrating of space-time performs operations, processing information in a way that could make our most powerful quantum computers look like simple abacuses. This idea emerges from a profound and still developing branch of theoretical physics that suggests the universe might not just contain information or allow for computation, but that space-time and gravity might be fundamentally computational in nature. To grasp how a gravitational structure could compute anything, we first need to reframe our understanding of what computation really is. At its core, computation is the transformation of an input into an output according to a set of logical rules. Your laptop does this by shuffling electrons through silicon circuits. A quantum computer does it by manipulating the delicate states of qubits, like atoms or photons, which can be in a superposition of both 1 and 0 at the same time. Now, what if the universe has its own native, physical way of computing? The laws of physics are, after all, a set of rules that govern how an initial state, a configuration of particles and fields, evolves into a future state. In this view, the entire cosmos is constantly performing a computation, with the present moment being the output of the past's input. The radical leap is to suggest that certain extreme geometries, like those inside a wormhole, aren't just outcomes of this computation. They are specialized, high-density processing units within the cosmic computer. This is where the nascent field of quantum gravity becomes essential. Our two great theories, general relativity, which describes the large-scale universe, and quantum mechanics, which describes the small scale, have long been at odds. A theory of quantum gravity seeks to unite them, and several of the leading candidates, like loop quantum gravity and certain approaches to string theory, hint that space-time itself might be granular or discrete at the smallest possible scale. It might not be smooth and continuous, but built from tiny, fundamental atoms of space. If that's true, then the dynamic relationships between these quanta of space could be seen as a form of information processing. The evolution of the universe would be the result of these countless elementary processors updating their states in relation to one another, a cosmic cellular automaton unfolding in real time. Within this framework, a wormhole presents a uniquely interesting structure. Its geometry is not trivial. It's a highly complex, non-linear warp connecting two distant regions. The intense curvature of its throat, the delicate balance of forces from the exotic matter propping it open, and the way quantum fields would behave within it all create an environment of extreme physical complexity. This complexity isn't random noise, it's a highly structured, dynamical system. Some physicists speculate that the evolution of quantum states as they pass through the wormhole's contorted spacetime could be equivalent to running a specific, immensely complicated quantum algorithm. The wormhole's geometry would act as the hardware, and the journey of information through it would be the software execution, with the final state of the information as it exits the other mouth representing the computed result. We can draw a fascinating, though simplified, analogy with a concept in quantum computing known as a quantum circuit. In a man-made quantum computer, you initialize a set of qubits, apply a sequence of logical operations called quantum gates, and then measure the final output. Each quantum gate is a controlled manipulation of the qubit states. Now, imagine mapping that abstract circuit onto a physical gravitational system. The wormhole's interior, with its unique and twisting geometry, could naturally implement the equivalent of a vast sequence of quantum gates. The path through the wormhole isn't a straight line. It's a winding, dynamic route where space-time curvature and quantum fields interact in a specific, prescribed way. A particle or a quantum field passing through would have its quantum state transformed by this journey in a manner that is mathematically equivalent to the particle having been processed by a sophisticated quantum algorithm. The wormhole in this speculative view is a factory-installed quantum circuit, its function determined by the specific way Einstein's equations have warped the fabric of reality. The potential scale of such a natural computer is what truly boggles the mind. Our current quantum computers struggle to maintain coherence, the fragile quantum state, for more than a few dozen or hundred qubits for any useful length of time. A stable, macroscopic wormhole, however, could potentially maintain coherence across a system of unimaginable scale. Every Planck-sized volume within its throat could act as a computational element, meaning a 1-meter-wide wormhole might effectively constitute a quantum computer with more processing elements than there are atoms in the observable universe. The computational power latent in such a structure would be beyond any form of artificial technology we could conceive of building. It wouldn't just be faster at solving problems, it could potentially tackle classes of problems that are completely intractable for any other system, such as perfectly simulating the quantum evolution of an entire galaxy or factoring astronomically large numbers almost instantly. This leads to a truly metaphysical possibility. If the universe is computational at its core, then the laws of physics are its operating code. A wormhole, as a specialized computational unit, might not just be a tool for solving equations we feed it. It might be an integral part of the universe's own operating system, playing a role in processes we can barely glimpse. Some highly speculative theories even suggest that the apparent fine-tuning of the physical constants in our universe could be the result of a cosmic evolutionary process where different bubble universes with different laws are generated, and perhaps only those with the right computational architecture, potentially involving structures like wormholes, become stable and complex enough. Support observers, in this dizzying picture, a wormhole isn't an optional feature. It's a fundamental component of a cosmos that computes its own existence, a knot in spacetime where the universe is busy running the most important calculations of all. Imagine a future where wormhole travel is no longer a dream but a reality. The technology exists, stable and proven. We've solved the quantum gravity equations, mastered the exotic matter, and built gateways to the stars. This moment of triumph, however, is not an end point. It is the beginning of the greatest ethical challenge humanity has ever faced. This brings us to our final and perhaps most urgent theory: the profound ethical and societal implications of wielding such power. For the ability to reshape our place in the cosmos comes with a responsibility so immense it could either unite our world or shatter it, forcing us to confront who we are and what we value at the most fundamental level. The first and most immediate fracture would likely appear right here on Earth: the problem of access and inequality. Consider the sheer cost of such an undertaking. The energy required to stabilize a single wormhole might exceed the gross domestic product of entire nations for centuries. The exotic matter needed could be a resource rarer than any precious metal, controlled by a single corporation or a consortium of the world's wealthiest governments. In this scenario, wormhole travel would not be public infrastructure. It would be the ultimate luxury good, a privilege reserved for a tiny, ultra-wealthy elite. We would see the birth of a new star-class divide, not between the upper and lower classes, but between planetary and interstellar humanity. A privileged few could step through a gateway to new worlds, accessing limitless resources, pristine environments, and potentially even biological longevity treatments developed in advanced alien labs. The rest of humanity would be left behind on an increasingly crowded and resource-depleted Earth, watching from the outside as a new aristocracy literally transcends the old limits of human existence. This doesn't just risk inequality, it risks creating a speciation event where one segment of humanity evolves into something else entirely, leaving the rest of us as a historical footnote. The social unrest, resentment, and potential for conflict would be unprecedented, forcing us to answer a brutal question. Is the starship or the Stargate a human right, or is it the ultimate reward for economic success? Beyond our terrestrial squabbles lies an even greater responsibility. The moment we confirm we are not alone, a wormhole doesn't just open up a new star system, it could open a doorway directly into the domain of another intelligent species. This is not a slow, decades-long radio signal exchange. This is an instantaneous physical connection. The protocols for first contact, which currently involve cautious listening and slow, deliberate messaging, would be rendered utterly obsolete. Our first hello could be a spacecraft tumbling out of a portal in their orbital space, an act that could be interpreted not as a greeting but as an invasion. The stakes are incalculable. We might encounter a civilization millennia more advanced than our own, viewing us with the same curiosity or contempt with which we view ants. Or we might find a younger, more vulnerable world and be forced to confront our own colonial instincts. Do we have the right to interfere with their development, even with the best of intentions? A single microbe carried on a spacesuit could trigger an apocalyptic plague on a world with no immunity. A well-meaning gift of technology could shatter their cultural evolution, creating a permanent dependency or triggering a global war. The prime directive from science fiction would become a necessary, real-world ethical framework, born from the terrifying recognition that our mere presence could be an existential threat to another world. The wormhole grants us the power of a god, but it does not grant us the wisdom to use it. Ultimately, the development of wormhole technology forces a mirror upon our own civilization. It demands that we solve our deepest problems here on Earth before we are fit to become an interstellar species. Can we manage this power without repeating the tragedies of our history, the exploitation, the conquest, the environmental devastation on a galactic scale? The wormhole is a test. It asks if we can overcome our tribalism and our greed to forge a global society capable of stewarding such a profound discovery for the benefit of all humanity, not just a select few. It challenges us to grow up, to evolve from a species that conquers its environment into one that nurtures and connects. The gateway to the stars is not just a physical structure, it is a passage to our own future, and the choices we make at its threshold will echo for millennia, defining whether we become wise stewards of the cosmos or just another fleeting, destructive flash in the galactic dark. And so, our incredible journey through the cosmos's greatest theoretical shortcuts draws to a close. We've ventured from the pure mathematics of Einstein and Rosen, which first revealed the possibility of bridges in spacetime, to the mind-bending frontiers where black holes might hide gateways and every entangled particle could be connected by a microscopic tunnel. We've explored the cosmic construction kit of exotic matter and phantom energy, grappled with the paradoxical nature of time machines, and even peered into the holographic source code of reality itself, where wormholes might be projected from a two-dimensional boundary. We've considered the possibility that dark matter and dark energy, the universe's greatest mysteries, could be the very materials that stabilize these passages, and we've dared to imagine a future where wormholes are not just transportation, but the universe's own ultimate supercomputers. From the tiniest fluctuations in the quantum foam to the vast, hidden networks that could connect entire galaxies, these 30 theories have stretched our understanding of what is possible, revealing a cosmos far stranger, more interconnected, and more wonderfully bizarre than we ever could have dreamed. While a stable, traversable wormhole remains a feature of our equations and our imagination rather than our observational data, its value is immeasurable. It acts as a powerful catalyst, forcing physicists to confront the deepest questions about the nature of space, time, and information. The relentless pursuit of this idea has illuminated the path toward a theory of quantum gravity, challenged our notions of causality, and provided stunning potential resolutions to paradoxes that have plagued science for decades. It pushes the very boundaries of human thought, demonstrating that the line between profound science and visionary science fiction is often the very place where the next great discovery is waiting to be born. The wormhole is more than a hypothetical tunnel. It is a symbol of our innate desire to explore, to connect, and to understand the ultimate architecture of existence. This grand tour of cosmic possibilities is just the beginning. The universe is filled with wonders waiting to be uncovered, and the conversation continues with all of you. We want to hear which of these theories reshaped your view of reality. Was it the holographic principle, suggesting we live in a projected reality? The ER equals EPR idea, linking every entangled pair with a tiny wormhole? Or the staggering possibility that our entire universe was born from a white hole in another cosmos? Let us know in the comments below which concept blew your mind the most. Your curiosity fuels this adventure. If you enjoyed this dive into the depths of space and time, make sure to subscribe and hit the notification bell so you don't miss our next exploration into the mysteries of the cosmos. Thank you for joining us on this journey through the gateway of imagination. Keep looking up and never stop wondering.